Good morning, everyone. I would like to welcome you on the second school on smart data processing and systems of deep insight organized by the Destini Horizon 2020 project. Thanks for joining us today. I am Dr. Panagiotis Christodoulou, member of the Destini's project team, and I will coordinate today's session. Today's session is divided into two parts. During the first part, an introduction about the Destini project will be made, and then interesting presentations on big data will follow. During the second part, our speakers will present topics on machine learning and blockchain technology. We will start today's presentations with an introduction from Professor Andreou, who is the coordinator of the Destini project. Professor Andreou, when you are ready, you can start your presentation.
Thank you, Panagiotis. Do you hear me and you see my screen?
Yes, yes.
Okay, thank you. So let me welcome you to the second online school on smart data processing and systems of deep insight, which is organized in the context of a Horizon 2020 training project called Destini. My presentation today will be very brief. I will make an overview of the Destini project, and then I will explain very briefly the areas of applied research that this project is focusing on. And I will close with some facts about the second online school. Some words, an overview of the project. Destini is a twinning CSA Horizon 2020 project, which started in 2019. We are currently on our third year. The Cyprus University of Technology is the coordinator of the project, and on board with us we have two leading universities, the University of Tilburg from the Netherlands and the Sapienza Università di Roma from Italy. The objectives of this project are three. First of all, to define a research agenda, a research strategy towards a set of research topics that revolve around smart data processing. The second one is to create, along with our leading university partners, joint programs for education, training, and mobility. And finally, to form a strong collaboration basis with stakeholders, strategic partners, market players, industrial stakeholders, and so on. And of course, with our ultimate target to be to engage SMEs and practitioners in order to be able to perform real-world experimentation and set up some real-world pilots. How is this vision of the project going to be realized? Actually, how it was and it currently is being realized through transfer of scientific knowledge, research expertise, and best research practices from the two leading universities to the Cyprus University of Technology. And how is this performed? Through the exchange of personnel, expert visits, site visits, organization of different events such as workshops and schools, the delivery of lectures, talks, and seminars from the leading universities to CUT and other events, joint events, and the mobility of joint educational programs of mobility and of training of stakeholders. Now, the Destini's research agenda comprises three different areas for applied research. Actually, these are three different areas, but they are integrated and intertwined. The first area is about smart data processing systems. You can see in the boxes the subtopics of each area. The second one is the area that deals with systems of deep insight, and the last one is a methodology for developing smart data-centric services and applications. All these areas, as I said before, are intertwined in a virtuous circle of research and build upon a strong framework for applied research, which is depicted at the lower part of this slide, in which we engage strategic partners and stakeholders. And this enables us to develop pilots that fall within the smart specialization strategy of Cyprus, and namely shipping, healthcare, food industry, and tourism. So how does all this thing work? We have the three areas of research at the right part. So the knowledge transfer and the expertise exchange is performed within these three areas. We couple these areas with Internet of Things, with technologies like digital twins, and this gives us the ability to set up pilots, as I said before, in a number of application domains. We can see here, for example, the smart healthcare and the smart manufacturing pilots. And how does this pilot work? We have a series of data sources, sensors. We collect the data. We put the data in a knowledge base, we filter them, we clear them, and then we perform smart data processing in order to be able to support decision making. Now, I should also mention that the project promotes the involvement of early stage researchers through a dedicated program we call Mobility Program. Through this program, the project aspires to attract ESRs. You can see the definition of an ESR by the European Union. So we would like to attract early stage researchers that will come to Cyprus for a period that normally ranges between 1 to 3 months. And these ESRs will join our team, perform research with us. So the project offers financial support for the relocation and, of course, a salary, a monthly salary. Now, coming now very briefly to the areas of applied research that this project has identified. The main areas are smart data processing, data lakes, digital twins, business process mining, and blockchain integration. These areas were identified as promising, and we have been concentrating our efforts during the last 1 year. Of course, there are other topics that emerge as the project evolves, but these are the main areas that we are currently focusing on. So a few words about each area. Smart data processing. We use the term smart data to emphasize the value that is inherent in widely unconnected, widely dispersed data sources. And our criterion here to characterize something as smart is not the volume of the data that are collected, but rather than the techniques that are developed to put meaning and context to this data. Of course, a basic parameter is to be able to understand data. So all this requires the development of specialized systems we call systems of deep insight. These systems are able to discover associations that are hidden in the data, for example, to discover large-scale patterns, trends, prioritize results, and so on. And all this information is used to perform some action. So this is something that enables us to react to this new information that is revealed through the systems of deep insight. The second area is data lakes. Data lakes data lakes are places in which we put collected data in a fast way and unorganized way in order to be able to collect the data very fast and put them somewhere in order to be able later to process them. So our research efforts here concentrate on building blueprints as a metadata mechanism that will enable us to characterize the data sources and then efficiently and effectively retrieve data from these data lakes. In this context, we are very much interested in querying the sources, creating subgraphs, utilizing visual query, applying classification algorithms or clustering algorithms, and to integrate data lakes with the blockchain technology to address some security, privacy, and data governance issues. In the area of digital twins, first of all, a digital twin is nothing more than a virtual replica of a physical device. We are very much interested in having these virtual replicas because we can then run simulations on the digital device and perform some a modification of parameters and study the behavior and so on without any cost. So what we have been doing in digital twins is we are trying to perform to enable an interaction between this mapping of the physical world to the virtual world. That is, we are trying to give birth to the so-called experimental digital twins. We have been using this, for example, in the area of smart manufacturing. More to that, we are interested in giving this visualization in an interactive manner, physical entities that will enable us to play with certain parameters in order to study the behavior of this physical entity. And of course, a graphical representation of real-world data that come fast from sources of these physical entities, and predictions that can be based on this real-world data that, as I said before, come real-time from these physical entities. The third area is business process mining. What is business process mining in a nutshell? It's an analytical approach that enables the discovery, the monitoring, and the improvement of business processes. How does this work? We get the logs from companies' information systems like the enterprise resource planning systems, customer relationship management systems, and we can recreate the business model and the workflow of certain tasks or activities. So Destini is focusing in this area on turning event data, logs, into insights and actions. So we actually do the typical stuff, that is project discovery and the creation of models such as PetroNets or BPMNs, but then we build upon these models and we try to analyze the business logs, the business process logs, perform, of course, typical conformance checking, but beyond that, to offer optimization and evolution based on predefined goals in an automated way, and utilizing computational intelligence, machine learning, and AI. And so far, we have been concentrating in applying these principles in smart manufacturing and the health sector. Finally, blockchain integration. We all know blockchain. I think from the wrong point of view, due to the hype of the cryptocurrencies. Of course, blockchain is much more than this. It's a fast-growing new distributed technology that enables us to record transactions on a distributed list of records that are chained together to form blocks. And of course, all this is protected using certain techniques of cryptography. So our focus is on integrating, bridging all the previous areas with blockchain. That is, for example, we focus on integrating experimental digital twins with blockchain, representing physical entities as NFTs, utilizing smart contracts to represent NFTs in 3D environments, and of course, bridging business process mining and data lakes with blockchain characteristics. Now, after this brief introduction into the project and the areas of applied research of interest, some facts about this school. This is the second school of the project. The first one was organized last year. It was also online due to the pandemic of the coronavirus. Both schools focus on smart data systems. It is characterized by many scholars and researchers as the future. It's the way we are currently and in the future going to work, entertain, live, receive medical care, and so on. Therefore, this is something very interesting and very important for our everyday lives. The second online school on smart data processing and systems of deep insight aspires to bring together students, researchers, companies, public organizations, and the general public in order to be able to share knowledge and experiences on smart data. But I would like to emphasize here that the focus of this school is on applied research. Therefore, all talks we are going to see here are focusing on the benefits that smart data processing brings to certain application domains. The duration of the school is 5 days. It starts today and ends next Friday. We have only morning sessions. We start the earliest at 9 o'clock local time, and we finish the latest by 2 o'clock noon. I would like also to mention that on day 3, which is next Wednesday, we have a sort of workshop. Basically, this day involves presentations of different case studies of smart data processing, different application domains, different application environments that reveal the power of smart data processing. A total of 33 talks, 33 presentations will be delivered by speakers from our university, from Tilburg and Yachts from the Netherlands, Sapienza from Rome, University of Cyprus, the Cyprus Institute of Neurology and Genetics, 3 local universities, Frederick, University of Nicosia, and the Neapolis University of Paphos, and some small to medium enterprises. The school is being broadcasted live from this link on Facebook. And also, we are recording actually the talks, and all the talks will be uploaded each day on our dedicated YouTube channel. And the presentations as PDFs or PowerPoints will be also available through our website. So having said all this, I would like once again to welcome you to this second school on smart data processing, and I wish you all, I hope that you all will enjoy the very interesting presentation that follow. Thank you very much.
Thanks, Professor Andreas Andreou, for the brief introduction on Destiny project. We will now move to our next presentations, which are focused on big data methods and technologies. Professor Donatella Firmani from the Department of Statistical Sciences, located at Sapienza, Università di Roma, will present the interested topics on big data. Professor Donatella Firmani, when you are ready, you can start your presentation. Thank you.
Ready. Thanks for the introduction. Thanks for organizing the school. Let me just make sure that everything can be seen properly.
Yes, everything is fine.
Okay, so you see. Great.
Thank you.
Okay, please interrupt me if anything goes wrong with the presentation. Okay. Here we go. Okay, so this seminar is based on different lectures by Riccardo Torlone at Roma University and some by myself at different university and Agenzia delle Entrate. Okay, so the goal of this talk is in general to provide an illustration of methods and technologies for the management of big data. So I guess everyone maybe is familiar with the notion of big data, but just to make sure we refer to big data when you have massive amounts of possibly unstructured data whose size exceeds the capacity of conventional database management systems. So capacity in the sense capacity to store, to capture, to manage, to analyze, and so on. So I hope that the main takeaways of this talk will be a general understanding of challenges and solutions, also technological solutions, some familiarity with the jargon in this field, and you will have some pointers to do more further research and study for more in-depth discussion on related topics. So what I will do is to illustrate general methods and use examples of popular technologies to describe those methods. So we will go through 3 parts. So we will discuss infrastructures, that will be brief. Then we will discuss big data processing more deeply, and then we will talk more about how we do understanding of big data in the sense of analytics, statistics, and in general the broader field of data science. So when data become big, we said that somehow you have this notion of normal processing capability, which is related both to volume and to the input-output operations per second. So we imagine that big data exceeds both dimensions of traditional management systems. So where do big data come? So big data come from a variety of, let me call them, technological phenomenon somehow. So we have the web, that is a massive producer and consumer of data. We all know how many tweets, search, messages we do online in the world, and the data is ever increasing. But also, that's maybe the widely known domain for big data, but this is not the only one. We also have somehow a proliferation of data sources. So the web is important, of course, and a main producer and consumer, but nowadays you have really many different sources coming from literally everywhere, from maps to traffic to pollution to health, water, and so on and so forth. So this idea of having many data sources is really key in the definition of big data. So not just one single producer, but a plethora of different data sources, and being continuously updated. So this is also referred to, in particular, this is also referred to the Internet of Things. So big data is really related to the Internet of Things phenomenon, where you have different sensors and you have objects that are connected. So not just the web, but really the Internet of the things. Big data can come from all of those sources. Okay, so big data is not about the volume. So of course, the volume is the main thing, but there are many other characteristics that are related to the process in which those massive data sets are produced. And those, you may know them as the 4 Bs of big data. So you have not just the volume, you also have the variety. In order to have all of those data, they come from different data sources. And for this reason, are really also diverse in format and in context. Some can be structured, semi-structured, or even structured as they were in the traditional data management systems. And together with those two, you have, of course, the velocity. which is the speed of generation that translates into the rate of analysis that you need, and the veracity, no? Because of course, all of those huge, massive data sets somehow need to be, are expected to be uncleansed, and due to the multiplicity of sources, possibly also untrusted. Okay, so we go directly to big data infrastructure technology. I won't have time to do an in-depth discussion here, but I will try to mention what are the most important technologies that are used nowadays and why, what are their pros and cons. Okay. So how do big data are created, processed, and analyzed? So you imagine that you have a data lake, which is a huge collection of different databases and datasets that you have access to. Big data come from all the multiplicity of sources that we mentioned, and they are loaded by using an ETL process, exact transform load process. And then after you possibly via also stream processing, not necessarily, but due to their velocity, possibly they're also processed via stream processing, and they're loaded, they're pumped into the data lake, if you will. And then you have the real-time processing and the batch processing part. So if you want to do analytics like reports or you do batch processing in general, and then you will use some technologies that we will see. Or if you have the real-time processing, maybe you can use both the NoSQL or the new SQL systems that are popular nowadays. So the new SQL is traditional SQL, but equipped with big data technologies. The NoSQL, we won't be able to discuss that in detail, but it's all the data management systems that are outside, let's say, the SQL representation, the relational representation. Okay, so how is the data lake characterized? So you have an incoming flow like the river, that is the multiple row that archives, whatever it is. Okay, can be also structured and unstructured. So you have flows incoming and making the lake bigger, and then you have the data set that you actually access to, which is possibly somehow processed, a little bit cleansed, and you really do maybe the analytics, for instance. Then you have the outflow of water, that is the analyzed data, and you can really eventually take your decisions. Okay. So the flow and the lake are typically implemented via two main architecture styles that are the Lambda and the Kappa. Okay, so the Lambda architecture, you have the layer where you do really the data streaming processing, and then you have a layer that is real time, where you have really the continuous update, and then you have a database where you access data both for real time and batch analytics, and then you have a query processor, which is possibly online, and then you have all the batch layer, all the batch layer that access the data, the real time serving DB, and updates a batch serving DB for the not necessarily online queries, but also batch analytics. So the Kappa is similar. Okay, the Kappa is similar, but is more focused on the streaming part, and you don't have the all the batch operations that are run here. Let's say periodically. So you might know those things and see in general implemented both Lambda and Kappa architecture, depending on how interested you are in the in this part. Okay, so if you don't are interested, go for K. Otherwise, you also have all the batch part with Lambda architecture. Okay. Where are we? So how basically all the storage and management of the resources is made. So things have been somehow changing and evolving these days. And you have maybe in the past decade, the main framework that was used by the majority of people, big data, was Hadoop. So you might have heard of this. So Hadoop is an open source framework where you can store and process massive datasets. And I mean, it is great, it is reliable, it is scalable, and can be used for doing distributed computing. Okay, so Hadoop is able to distribute both the storage and analytic workloads, and it can do across multiple nodes. So the thing here is that those nodes where you distribute storage and analytics that handle the work parallelly do not need to be high-end systems, can be really commodity hardware or really almost low-end hardware. This made Hadoop very popular, and then we'll come to that in a minute. So you can have fast and low cost together data processing capability. So Hadoop consists of different modules. The main module is the distributed file system, so HDFS. So this file system can run indeed on low-end hardware, and really can provide significantly better output than traditional file systems, and somehow was built to promote fault tolerance and the ability to handle large data sets. So of course, this is not the main module, but this is not the only module, but it's the module that made maybe Hadoop so popular. So notice that the Hadoop one is not the only distributed file system existing. So there are several distributed file systems that are used in practice. So let me mention some of them: Google File System, or the Cloud Store, or many others. Okay, so Hadoop was somehow one of the most used in the past decade. So Hadoop is not the distributed file system. You have other modules. So other modules include Yarn, MapReduce, and Hadoop Common. So Yarn is the resource manager for the cluster. Okay, so it's really what makes the coordination of all those nodes, those computing nodes possible. Okay, so handling also failures and so on. Okay, then there is the MapReduce. That is another popular name that you may have heard of. And so the MapReduce is really the processing engine. So see, Hadoop is not just the storage. It really comes with its own processing engine, also for doing big data processing, and really it's a new programming model, and we'll come to that in a minute. And it's designed to optimize the parallel computation. Okay, and this is only the only processing engine that is available on Hadoop. So on Hadoop you can plug also other engines such Spark that we will discuss later, but it's the default processing engine. And then there is a common set of libraries, which is useful to use across multi-modules. Okay, so what are the strengths of this framework? So we mentioned that somehow it's the scalability, of course, and the flexibility. No? Why the flexibility? So Hadoop can collect a variety of data types, and you don't need to have to go through the process of converting data into a single format. It's very flexible to work with different inputs, so you can have, see as in the Lambda and Kappa architecture, different stream data, social media, internal collection, so you really designed to work with the data lake as it is typically structured, and you can have structured and unstructured data, and really it's very flexible. This made Hadoop very popular to use. Of course, there is also the scalability part. It's excellent for batch processing, so when you have all of those data types in the lake, in the DFS, you can have great routines for doing the batch processing as in the Lambda architecture, okay? And basically the scalability in the sense that you can really store data in a sense endlessly. So imagine that you have your variety of data collection, you do batch processing, and all the unprocessed data, you just, so all of those things in the flow that then you don't use to do your main lake, you can just store them and reference all data easily, and the storage is really minimal because of the discussion on the commodity hardware, so you don't need high-end hardware infrastructure, okay? So people loved all of those features. Of course, this comes with few shortcomings, okay? So in a sense, and the fact that it is designed to process all those large-scale data sets makes Hadoop, in the sense, not suited for handling small data sets. But that really needs to be interpreted literally. If you want to do a quick analytics on a reasonably small data set, using Hadoop is cost prohibitive, both for the resources and really because it is not so friendly to set up everything, okay? So a user really needs to be motivated to use Hadoop and really have the need for handling those large-scale data. So if your data is not so large-scale or it is even small and you want to do something quick, so Hadoop, that's very possibly not for you. And a lot of people had both scenarios occurring at the same time. So for one scenario, Hadoop was great. For another, Hadoop was really not suited, okay? And people had to come up with other solutions. Then another shortcoming is that, so remember there are other modules of in Hadoop, including Yarn, the resource manager, and you need to use that, okay? So if you want to do something, and those are all Java-based technologies, so of course there is support for other languages somehow, but mainly everything is Java-based. So if you want to do something like, I don't know, mixing those kind of frameworks like data warehouses with Redshift, BigQuery, Panoply, and you want to move things around and put together in the same place, you can do that with Hadoop, okay? And finally, I mean, there are other shortcomings. I selected those three because those seem to me the main ones. And finally, you really have no easy way to output data that is related to the fact that it is not suitable to do quick analytics somehow, but not only, okay? So you remember, you have the distributed file system, you have the data processing engine, the default one that is MapReduce, and you can plug for others. But for output data, for looking at your data and doing the last part in the data flow, remember there was at the end you want outflow of data and you want to look at your data. That part in Hadoop is not provided, and it's not too easy to integrate other technologies with it, and somehow making Hadoop not the best for business intelligence teams that want to make visualizations, reports, and so on. So, I mean, it's not that people don't use Hadoop anymore. People keep using Hadoop, of course, But people started to consider other infrastructures. I will provide you maybe a quick picture, the landscape of technologies that there is right now. So one thing that is not really something that substitutes Hadoop, but it is another popular technology that people start to use to deal with the variety also of technologies, not just of the dataset, of technologies that are used for handling big data, okay? That is Kubernetes. Okay, so on the infrastructure side, somehow people are trying to do cloud native applications, and so that sparked the usage of other tools that are not really from the Hadoop landscape. So indeed, if you want to do those things with those cloud native application systems, you really can do everything very easily through containers. And of course, you can leverage all the resource maintenance facilities that you find in the cloud. That's for the infrastructure. For the processing, the MapReduce module has been progressively became progressively less popular in favor of other systems like Spark. So remember, Spark can be used together with Hadoop, but you can use it also with other systems. So it's something that it is can be used very well together with Hadoop, but not necessarily. So, and that's really one of the main, the most popular technologies that are available right now for the processing of the big data. And we come to that more in detail now. Okay, so if you want to interrupt me and ask questions, feel free to do that. Okay, so just let me know if you want me to go more in details into something or want to ask questions and interrupt, you can do.
Thank you, Donatella. Do we have any questions from the crowd?
Say this again.
I'm just asking if we have any questions from the crowd.
Ah, okay.
It seems that no one wants to ask something. Let's see at the end of the second part also if someone wants to ask something. So you can continue. So then we're going to have okay, yeah, you can continue, and then at the end we can raise the questions at the end of the presentation. Thank you.
Okay, so just a quick comment on the scheduling. So do you want, so we will have a break, right?
Basically, the break is after you finish also the second part. So
okay.
Yeah, so you can continue, and then we have, if we have any questions, and then the break. Okay, great. This is at 11:10, so in 1 hour basically the break, the first break. Thank you. Okay, so we'll have, sorry, so just to be sure, because there was some okay, so we do a short break, let's say around 10. Sounds good? Yeah, basically the break will be conducted after you finish your second part, then the questions, and then we have the break. Okay, good. Okay, thank you. Thanks. Okay. Okay, so one thing that is that people like to use for doing processing is Spark. Okay, so Spark, it's not really, as I said, it's not like a Hadoop Plus. It's something really different. It's a separate engine. And really the idea is doing an engine for data processing. So it's MapReduce-like, and we'll see in a minute why.
but it is very different both in the programming model and in the implementation, and that that is currently very popular among people. So it's both more flexible in the programming model, and it's really faster. And of course, everything is compatible with Hadoop, and you can really run it literally on top on a Hadoop cluster, so where also things are represented with the distributed file system by Hadoop. Okay. So the project, it's more than 10 years old. So it started in 2009, then open sourced it, and then became an Apache project from 2013. And it's among now the most popular projects for processing. So I haven't introduced the notion of MapReduce programming model because it is maybe reasonably known, but let me just, to make everything self-contained, make a quick comment on how it works. So the idea of the MapReduce system in Hadoop, okay, that's the general idea of the MapReduce programming model that is implemented in the MapReduce engine by Hadoop. So the idea is really that you change your programming model in the sense that you want to describe everything that you need to do with your data processing via two subroutines. You have the map and the reduce. So that has roots in functional programming in the sense that there was this paradigm of doing mapfold or MapReduce programming, where you really have those two functions. And everything can be done with those two functions. Everything can be represented as multiple rounds of executions of those two functions. So for instance, in the map, you have a data set, let's say a list, a sequence, or a collection in general of items that are data items, can be as big as you want, depending on what you want to do with your program. Your map function applies some logic to every element in your list, in your collection, that produces another list, okay, that can be different from the input one. And you have then the reduce operation that it is instead meant to aggregate the results. Okay, so you have this map and aggregate steps, and you can do a variety of things efficiently with this model. Okay, so that was implemented in the MapReduce engine, especially the MapReduce engine that it is available in Hadoop. It is not the only MapReduce engine that you find around, but it is one of the most used one. So Spark somehow keeps those roots, but adds on top of it really a new and more general programming model. So that means that boils down to the fact that in Spark, you don't have only map and reduce. You have a variety of functions that you can apply, and we'll see those in a minute. So MapReduce was great, and people used, you might have heard of the popular word count example, and was very popular because it really greatly simplified the processing part, okay, and also made simple also to express things with the parallel processing in mind, with a parallel processing mindset. But as soon as it got popular, okay, people wanted more. Okay, so everybody wanted to do things with MapReduce, even things that were not so easy to do with those two operations, map and reduce. So people started to come out with multi-stage applications. So I also been working on those things. So you were planning to, so you wanted to implement those some complex graph algorithm with doing everything with the mapper and the reduce so that they could run on a Hadoop cluster very efficiently. So that was reasonably hard. So you had to design some really clever and sophisticated ways to do iterations of different map and reduce things to really realize the original logic, same for machine learning. And so map reduce application became progressively more difficult to understand, share, and use even, okay? And even less efficient, because, you know, as you force a system out of its designed scenario somehow, things got less efficient. And for instance, in MapReduce, when you do in the original MapReduce engine, like the one in the Hadoop, if you do multi-stage in the sense that you do MapReduce, then MapReduce, all those stages take time and cost efficiency, in the sense that at the end, things are start to suffer and scale less well than needed. And so Spark came with a new programming model for support of multi-stage interactive application and all of those things. That really required to change the idea of having those two functions and doing something more more flexible in a sense, okay? So the key idea of the programming model in Spark is the RDD, okay? So the RDD is a data structure. It is the resilience distributed data set. So you have, basically it is a data structure that works as a distributed memory abstraction. So that lets the programmer perform parallel computations on large cluster somehow transparently. So if you are able to express your program using operations and the API of those RDDs data structure, then you can do a successful Spark program. So those RDD can be cached in memory, okay, can be manipulated through different operators, not just map and reduce. We'll see that there are more of them. They automatically rebuilt, so you have all the reliability that you had with the Hadoop in the Hadoop world. You can persist them in memory, you can partition them, you can do a lot of things. And they have a very clean interface that it is exposed in different programming languages and can be neatly integrated with those programming languages. For instance, Scala and Python, among the most popular ones. And then you also have Java and R, and can be used interactively from the Scala console. So if you are a Scala lover or a Python lover, you can really use Spark in your program without really somehow even realizing that things are working on a cluster. So if you are ever used Hadoop in your life, you remember that you had to package map and reduce programs into jobs, then upload the jobs, manage the execution of the jobs, and it was really more it was really less user-friendly somehow. Here, when you use Spark, you have a Python program that really looks like traditional Python programs, but things are working in the cluster through these nice abstractions. Okay, so really, you have the following. So applications run as independent processes on a cluster, and they're coordinated by an object that you create in your main program. So you have a Spark context object you create in your main program. We'll see a snippet, an example, okay? And in order to do everything, you connect, so the context object connects to several types of cluster managers, including Yarn. Okay, so you can reuse the cluster manager of Hadoop, but you really have this more abstracted layer through the context where you can skip working through different, maybe more complex operations that you as a data processing programmer don't want to manage directly. Okay. Then when you connect, the Spark system selects executors on nodes of the cluster, and those actually run the computations and store the data. Okay. Then it sends the application to the executors, and the executors will effectively run. This is all managed by the Spark context object that will send those your code, specifically tasks related to your code. Okay, so how does it work? We won't go into too many details, so we just see as an idea things how they can be implemented. So say that you have this driver program, and this driver program can be part of a longer Python or Scala program, and you don't even notice that you are sending things on the cluster, except for the Spark context, of course. Okay, except for the Spark context object that you have to create. Okay, so you have your program, you have your Spark context object that create, then you create your RDD from a dataset that you are interested on. Okay, and then after that, you can apply a variety of functions, including the map and reduce functions, on your RDDs to implement your processing logic. Okay, so then the Spark context will go, select resources on the cluster through the cluster manager that, again, it can be Yarn, it can be, everything can be an Hadoop cluster, or even not. Okay, so that's the flexibility. You will connect to some worker nodes and then send the tasks, eventually accessing, if you are willing to use an Hadoop cluster, HDFS. If you are not willing to use an Hadoop cluster, then will be differently. Okay. Okay, so the main thing, apart from the Spark context, that it is fundamental for accessing the cluster resources. So the core of the programming model in Spark is this RDD. Okay, so as we said, the RDD is a data structure that it is fault tolerant, distributed, and you can have controlled partitioning, and especially why it is interesting, because it can be manipulating using a very rich set of operators. What does it mean that you can use a rich set of operators? It means that other than map reduce functions, you can do many more functions, and that there is even more. We'll see that. Okay, so what are those operators? So those operators, you have this rich collection of operators that you can use in Spark, and you can implement very easily a variety of processing logics on your data. Okay, and those will be run very efficiently, like even 10% faster than other processing engine like, for instance, MapReduce. Okay. So how do you do that? You after you specify your operators, okay, so your program will be in a sense compiled into a directed cyclic graph of operators, okay, and that graph will be really what will be executed on your cluster. Okay, let me show you concretely what kind of operations of operators can be included in the directed acyclic graph. Okay, so you have mainly three types of operations that you can do on the RDD. You can do transformations, you can do actions, and you can do persistence. So the transformation is what really want to do. So remember the remember what was that, the big data processing. If you remember at the beginning, we have been looking at the data flow, okay, of the data flow of big data. You really have the let's say downstream processing that eventually becomes analytics, but you also have the upstream processing that it is truly the all the extract, transform, and load operations that you want to do on your data, on your incoming flow in the data lake, really to populate the lake. So, and you here have a variety of transformations that you can do, okay? And also have transformations that you can do for doing more advanced computations, eventually becoming the basis for your analytics and your visualization to run. So when you do transformations, you create RDDs, okay? So those transformations are lazy in the sense that when you specify them in the program, those are not executed, okay? So they are executed only when you have actions, okay? So when you do actions on your RDDs, those really trigger the computation of transformations. So say that you have, so examples of transformations are map and filter. Okay, so say that you want to filter an RDD. So that filter won't be executed until on the same RDD, you will execute some action that is meant to extract a value. Okay, so say that you want to do filter and count, and in the program you have different steps. At some point you specify the filter, way below you specify the count. So everything will be run when the count is executed. So when you encounter the count, then you will do all the transformations that come before that count in order to make that count actually computable and return a value. So that's why really you have your program that becomes somehow a graph of operations. Okay, and then you have the persistent. The persistent can be used for like disk storage, for instance. Okay, so let me go more into detail. Okay, so we said the transformations, actions, and persistence. So transformations, operations on the RDD return other RDD objects or even collections of RDD. So a simple transformation that you can imagine is the filter. Okay, so if you have a RDD that it is really a collection of values, okay, you filter some, or you do the join, or you can do a map. Okay, you can do all of those things to transform an RDD into others RDDs or even collections of RDDs. And those are lazy, okay? So it means that they are not executed immediately, okay? Actions, as we said, take as input RDD, okay? And return as output, say, value. Okay, so a value, meaning, for instance, a count. Okay, say that you want to filter and then count, you can do through actions at the end, or you can even have reduce, or you have a rich collection of those. And those are, as we said, so this is lazy, this is synchronous. When they are executed, so when you have an action, then you trigger the execution of all the transformations that have been specified for that RDD, okay? And really, I mean, so I'm saying somehow, maybe sorry if I'm saying multiple times, but until you have no action fired, the data will won't be even accessed. Okay, so actions really materialize the entire process with data. And finally, you have the persistence, okay, because you want eventually those RDDs maybe to be stored somewhere and not just being created for intermediate processing steps, but maybe you want really to save them in your, say, data lake, okay, or even not just because you want to persist them, also because you want to optimize the execution, okay? So for those two reasons, you want to persist that RDDs somewhere, okay? Indeed, by default, every time you run an action, okay, the RDD is recomputed, okay? Is recomputed, you reapply everything and do the action finally. So that might not be the most efficient choice, depending on what is the flow that you have in mind for your processing. And sometimes maybe it's useful to persist RDDs to optimize the computation. So it's really something that is very important is Spark. Okay, so when you persist the RDD, the nodes stores significant portions of it, and that allows future actions to be much faster, because when you rerun an action, you won't have to recompute everything, and you really can mark an RDD to be persisting using those operations. Okay, so at the end you will, so the first time you compute it explicitly, then you keep it in memory. Okay, and of course that caching system, okay, is fault tolerant in the sense that if any node has errors or if any partition of the RDD is lost, then it will be recomputed using what? Using all the set of transformations that you originally used to create it. So that's why it really implements a reliable and fault tolerant distribution logic on the cluster. So see everything, you don't have to work to program this explicitly. All those functions, including the persistence, okay, are offered transparently through the RDD data structure. So the only thing that you, programmer, need to do is really to rethink your programming logic as a sequence of transformations and actions on RDDs, as you had to do with the MapReduce functions, but having much more possibilities, many more operations that you can use. Okay, and that also accounts, as we said, it's okay to do even for small data sets, so you don't have the huge overhead that you had for using the entire Hadoop system, including the data processing module. So that was big overhead for small data sets, low support for online and streaming or interactive querying. All those limitations that you had in Hadoop, here you don't have. If your dataset is big, great, Apache will be faster. Okay, if your dataset is small, you can still enjoy the selection of the Spark programming paradigm and use it as you see fit. Okay, and even if you need something that is interactive, maybe by using persistence, you can optimize things and you will have a fast running application irrespective of the size of the dataset. Still, you can use the low end computing infrastructures as in Hadoop by putting everything on top on an Hadoop cluster, which is really some very popular solution that people use in big data processing. the Spark on top on Hadoop cluster. Okay, so everything is doable. Everything is realized by computing the directed acyclic graph of operators that corresponds to the program, and then compiling the directed acyclic graph as a series of tasks that will be submitted to the workers by the cluster manager as indicated by the Spark context object that you initially created in your program. And remember, all the actions drive the execution. Okay, so let me show you a simple example. So this is Scala, and this is the popular word count example that all the people learn when they start first using Hadoop and MapReduce. Okay, let me just mention, if you haven't already heard of it, in the word count example works as follows. So you have a series of words, like a collection of words coming from a text, for instance. Say that you want to compute the frequencies of those words and see, for instance, which one is the word that occurs more frequently, for instance. Okay, you can do that via plain MapReduce. So even before Spark, you can do that by plain MapReduce by specifying, by mapping every word, let's say, to somehow say itself. Okay, and then you can reduce by key, in the sense that you take all the occurrences of those words that are mapped to the same reduce program, and the reduce function, the only thing that needs to do is really counting all the occurrences of the same words that it received, and then finally return the result. So that can be expressed in MapReduce by saying map maps words to itself. Reduce takes a collection of words and just counts them. Okay, that can do even before Spark, but you can do that even with Spark much more easily, so with less less code, less interaction with the cluster resource systems, and much more efficiently via the RDD. Okay, so what are the operations that you will use? Will be map and will be reduced by key, and then you have the here you have the save as text file that really will persist all the counts into memory. So that is in Scala. If you are more familiar with the Python syntax, that's very similar. So see here, you are creating your data structure that will work as an abstraction of all the distributed processing. Okay. Then you apply a transformation. Okay. And then you apply an action. Okay. And then finally, you take the really value that you take that you have eventually that you can eventually collect in your RDD. These triggers everything. You take the output and you can save it as a text file. Okay, so that is really like 3 lines of literally 4 lines of codes. Okay, so see, remember the transformations that we have seen. Okay, so this is the transformation that you have, and then you have 2 actions that are reduce and collect. And then you have the final action that is the save as. Okay. So here in this example, you have the reactions and a transformation. Okay. Okay. So hopefully that convinced you that it's worth to start learning all these programming abstraction for processing large-scale data or even small-scale data, but just to have this scalability by design in your application, okay? But sometimes, okay, so that is a reasonably complex machinery that allows you for computation not just of plain extract, transform, load, but you can really implement a more complex processing and eventually really do analytics, okay? So that is great, but sometimes you really want to do something somehow easier, no? You want to just do plain extract, transform, load, okay? So if you want to do that, perhaps using Spark might, especially if you're not familiar with the programming model, can be somehow needs to invest a lot of your resources to understand how to do that. There are other tools that provides a very intuitive syntax, okay, for doing some various transformations on data, and can be used really to do very easily initial or even intermediate steps of the data processing of the big data workflow. Okay, so if there are, I guess that many people, even among you, okay, are familiar with the SQL syntax. Okay, so if you are familiar with the SQL syntax and are asking why, if I have a big data, I cannot do just, I don't know, distinct count instead of, or even plain group by operations rather than all these map, reduce, collect, actions thing? The answer is yes, you can use other. So you can even use real SQL, like using all the new SQL infrastructures, but there is also the Apache Pig tool that it is something intermediate. So the syntax that provides is SQL-like. Okay, we'll see that. So we will see some examples in a minute. But what you're really creating is something that is imperative. Okay, so you are creating an imperative program. Okay, so it's not like all the new SQL. All the new SQL systems are SQL systems, okay, like with schema, with queries, with query plans that are automatically computed. The only thing that run on clusters, okay? So here you are not doing SQL on cluster. You are doing something that is SQL-like, but still you are doing imperative programming, okay? And what you will end up with is, in a sense, an abstraction for creating those MapReduce programs, okay? So, and you don't need a schema for that, okay? So you can easily represent semi-structured data as typically occurs in the incoming flows of the data lake. Okay, let me show you why it is very easy to do, to use. Okay, so rather than going into the syntax in detail, I will show you an easy working example. Okay, and then we will stop for a break and then finally go to the last part. Okay, so say that you want to, that you have two data sets. Okay, so you have two data sets, like a list of words with their frequency of appearance on web pages. Okay, and then you have another list where you have users and web pages they visit. Okay, and you want to do the following: given the words appearing in web pages and giving the users visiting web pages. So you want to know which words the users might be interested into. Okay. So suppose that you have this data set. So here you have the website. Okay. So your data set is structured, but can be different. You don't really need a schema, a database schema as in SQL, we'll see. Okay. So you have the website. See here you have a sequence of websites. For every website, you have a word and a frequency of the word in that website and a date that represents the timestamp of this tuple. Okay. So for instance, here you have in the CNN website, you have the Trump word with that frequency up to 17 October. You have also the, say here, the climate word in Reuters with that frequency up to September of the same year, and so on and so forth. So you have a collection of websites. For every website you have, so that's why websites may appear more than once. You have different words and the frequency of that word in the website up to a certain date. Okay. And then you have this other collection that can come from CSV or from whatever source, or can be even already in your data lake. Okay, and there is the user and the website the user is interested to. Okay, so say that we want to understand, for instance, that Bill might be interested into climate. No, because it goes to Reuters and Reuters has a lot of climate word frequency. Okay, so that's the final goal. Okay, in order to do that, of course, I could do different things. So I could write an entire MapReduce program and represent it and pack into a job that will be run on Hadoop cluster via the Yarn. So that was the, let's say, 1 decade ago solution. Okay, or I can write a Spark program using my favorite language, for instance, Python, create RDDs out of those datasets, and apply transformations and actions to compute values. And those values will be a representative of words that might be interested on users, okay, as we see, or I might even forget about all those abstractions and programming modules that come from the functional word, that have roots in the functional words, like we see the MapReduce and so on. And maybe I like SQL, and I can write a pig-Latin program on the Apache Pig system as follows. So see, I load the dataset. Okay, so here I'm describing the character that is the limiting columns. Okay, and I'm loading that into these, let's say, structure. Okay, with those attribute values, with those attributes. So I have the word, freq, and date. So here, the dataset that can be plain text and come from whatever or be represented into a CSV in my data lake becomes a data structure with tuples. No? And I've named the attributes as I see fit, website indexed, word, freq, and date. Okay. Then I might want to do some cleansing, as we said in the big data world. Typically, remember the 4 V's. There is the veracity, typically dataset are unclaims. Okay, for instance, here we have some repeats. So the fact that, so the frequency of climate in Fox News is referred to into different rows on my dataset. The frequency of climate in Reuters also is referred to into different rows. So I want to clean those up, and I can do the distinct. So I can do really the distinct of the dataset and obtain. See, it's imperative. So things are really programmed into with an imperative fashion, and I can obtain a new data set which having no duplicate data. Okay, then what I can do maybe is look more into my data set and see that there are some rows that are old. So the frequency of climate in Reuters is maybe updated, was updated in September. Okay, so in September maybe I see that's too old, maybe things can be can have changed in the meantime due to the velocity of the data and how things evolve quickly. And so maybe I get rid of all the tuples that are that have been collected before this date. And maybe I also get rid of words that have a very low frequency. Okay, so because I don't want to recommend words to users that have very low frequency in their original websites. Okay, how can I do that? I can do a filter. So that could have been done very well with a Spark program. Here I'm just representing an alternative because every technology can be used, depending what are your preferences, also in terms of programming, and also what is your goal. Okay, so here I can filter by date and frequency. Okay, so I get rid of everything that has date before October, and also I get rid of everything that has frequency below point equal or below 0.002. Okay, so that leaves me with a very clean data set where I have the most significant and recent frequent count of words in websites. I have no duplicate, and I have everything that it is ready in my data lake to be finally maybe combined with other data sets. Okay, before doing that, I get rid of some attributes, maybe because I don't need those. After I was needing them only for the processing. Okay, and that can be, I can do the project, the filter, and then also the project, and I remain with those pairs. And finally, I can do the join. Okay, so here I have a website to users that was originally provided in this form. Okay, so here I just loaded without doing any cleaning or distinct operation. And then here I have my cleaned website as words dataset. Okay, and I can just join them and get for each user what are the words he or she might be interested. So I can suggest Bill the word economy. I can suggest James scheme, COVID, and WHO, and so on and so forth. Okay, so everything, of course, was doable with the Spark program. Was not so easy with a MapReduce program because I If I wanted to do that, I had to prepare for doing multiple job iterations. I can do everything very neatly with the Spark program, but if I like SQL syntax, I can do everything even with a pigletting program. Okay, so I was somehow forced by time to select those two tools that are Spark and Pig for data processing. Here finally I have the group by, of course, and really what was represented as a list, I can represent it as a list with lists more explicitly. So for each user, I have the list of words the user might be interested in. Okay, I can just write, see the syntax is very SQL-like, group by. Okay. So the whole pigletting program looks like this. Okay, of course, if you want to have fun after the talk, you can try to do the same, not as a pigletting program, but as a Spark program if you want. Okay, with Python, for instance. That is a nice exercise that you can do at home if you want. And if you have doubts, you can just send me and we can discuss offline. Okay, so I was forced by time, as I was mentioning, to select Spark and Pig as the main, let's say, as two popular big data processing tools, but there are many others. I selected those because they are representative of two different approaches to do the same, let's say, transformation part of the big data processing flow, as we have seen in one of the first slides. But there are many others. But just to give you, and I'm sure that there is among you somebody that has their own favorite technology, and then now he's asking why I'm not mentioning those, but it's very, I mean, there are many technologies in the big data landscape, and just to give you like a feeling of how fast everything is growing, I suggest you to look on the web for these big data landscape resources by those two web users. Okay, if you look for the big data landscape resources, you will find something that was maybe updated to 2012, and that was and it looked like this. Okay, so you have the infrastructure technologies, you have the analytics technologies, applications, data sources, and open source projects. And here you can find the pigletting, that is in the programmability section. And here also the Hadoop distributed file system. Okay. After 2012, let me show you in 2016 how the same landscape was looking like. See, it's much bigger. Now you have Spark, you have again the HDFS, you have pigletting, but you have many others. See, you have a lot of NLP, machine learning, and business analytics resources. Okay, so if you look at the same resource today, the big data landscape is looking like this. Okay, so here you can see the infrastructures we mentioned so far in this talk, but you see that there are so many others that is impossible to cover. Okay, of course, that provides you let's say a starting point to look for your dataset favorite technologies, depending on whether you are interested in the infrastructure part or the analytics or processing. Okay, so sometimes you find analytics and processing that are somehow overlapping, and then you have a wide range of open source projects for doing many tasks, including also security and data access and many other also programming models and different approaches to do to take value out of the big data datasets collections. Okay. Okay, so before we dive more in how really we take values out of big data, okay, let me explain stop for a minute.
Yeah, Professor,
Sì?
I just wanted to tell you that we have just 5 minutes. So if you can go it a bit quickly.
5 minutes?
Before the break, yes.
I can have the break now.
Yeah, but basically after the break is a different presentation.
Ah, okay. After the
So,
okay.
So you can take, let's say, up to 10 minutes, and then we're gonna extend a bit of the break later. So in order to finalize.
Okay. No, it is good. I can. Okay. So
Thank
here
you.
I have basically like 15-minute slides, but I will compress things. Indeed, I'm 5 minutes late. Indeed.
Okay.
I have basically.
We cannot see your screen now.
Okay. So I will compress. Sorry, I will compress my 15 minutes into like 7 minutes.
Okay.
So everything will be on time.
Thank
Okay.
you.
So let's say misunderstanding was that break in the sense that break within my talk and break among my talk and other talks. Okay, so let me go through to understanding big data. Okay, so here I will go slightly more quick than planned, but hopefully things will be clear anyway. Okay, so we have the value. Okay, so we said that we want to extract value out of big data. Okay, in order to extract value out of big data, we need to be very aware of risks of bad interpretation. No? So of course we can have huge competitive advantages, but we need to be aware of risks of bad interpretation. So here there is a funny comic in order to wake up and prepare for the break. So if you have sales and shaved heads trends that are correlating, you don't want to take a razor in order to improve your sales. Okay, so there is this whole entire new discipline of data science that can be broken into analytics, statistics, and ML/AI. And of course, there are big data tools for every of the three. Okay. I will briefly present you. So just a short disclaimer. Of course, analytics and data mining are really overlapping. So I'm presenting those three as three pillars, but there is some overlap among the three as well. Okay. Okay, so which one are you interested on? Do you want to learn to do analytics with data? Or do you want to learn to do statistics with big data? You want to learn to do machine learning with big data? Of course, you can you can choose your own data science adventure according to what you want to do. Okay, so say that you have you want to make decisions, so your mind is set, and you want to change your mind possibly after evidence, if there is uncertainty and you need to take few decisions, very important, and maybe you want statistics. Okay, so or if you want to take lots and lots of decisions using data, maybe you want to go with machine learning. Or if your mind isn't set yet and you're looking for inspirations, or you're looking for really a way to storytell your data, and then you want really analytics. Okay, so let me just mention you for fun that there are people, and I'm among those people, okay, and somehow analytics is somehow a misunderstood hero in data science, because people want to just come out with models, and they really maybe spend less time by looking actually into the data, so studying visualization tools or data mining, or really even data aggregation. Okay, so for doing analytics, there is a huge range of technologies. So from the Spark itself to all the libraries that can be used for running algorithms on the data in order to summarize the data that you have into interesting facts. that you can use for inspiration, and then maybe identify hypotheses, so identifying opportunities, and providing input to decision makers. I will mention you one specific category of tools that is for a graph algorithm. Okay, so you might have heard about network analysis. So many of the data that you can have can be shaped as a graph, for instance. So data can be structured, shaped as a graph, for instance, and suppose that you have those kind of data and you want to do analytics on those kinds of data. So you can use a wide variety of tools that you can run on top of other tools that I mentioned. And basically what you want is a graph DB. So you want a graph database systems, and there are many of them that are able to let you ask queries to the data to take inspiration and summarize the data into interesting facts, such as, you know, find the book in the database category that are written by someone whom friend of mine likes. No, you can write all those queries that would be very difficult to ask with the traditional data management systems. Okay, and you model the data graph. You can have many, ranging from those queries to very complex queries like reachability or other graph analytics tools. Okay, and there are many. I'm suggesting those to start with, but there are many others. Those are for storing GraphDB and for asking queries. They come with their own querying language that is, it's called a Cypher. It's reasonably easy to learn. Okay, if you want, I can provide you pointers too. I was not planning to go into the Cypher language, just to show you that it is very easy. And there is also, together with the graph database systems, there is also a wide range of graph algorithm library for running not just queries, but complex graph algorithms that can be used, for instance, for social network analysis or for other analytics and mining tools such as Pregel, Giraffe, GraphLab, and HAM, and there are many others. Okay. Of course, if you are not interested into the analytics part and you want to go directly into machine learning for big data, there are other tools that I'm not going into this talk. You can look for them on the web, and maybe there is also the mlib suite that is integrated into Spark, that you can successfully and easily use on top and running on top on Hadoop cluster. And finally, if you want just to do like statistics and you are more familiar with R, okay, you can keep using R in your big data infrastructure, because there are ways of running R on clusters, okay, such as R Hadoop or Evolution or Spark R. Okay, so if you are familiar with R, you can keep using that and use, for instance, the same R running on Spark. So say if you learn Spark, you have a processing tool, then you can use, for instance, mlib Spark for doing machine learning, or you can use Iron Spark for doing statistics, and you can integrate that with an analytics selection of analytics technologies for doing, for instance, graph analysis or other analytics tool, and you really have your architectural stack for big data at a reasonably low cost. So conclusions, as I promised. Okay, so conclusions, we live in the era of big data, and as I hope I was able to let you know, there is a wide range of possibilities and availabilities of data, and thus opportunities. Okay, of course, by processing those data, you can extract and access value. It's not easy to manage and use them somehow, because depending on the toolkit that you choose, some things will be easy, other things might become hard or even unfeasible. And so both methodological and technological aspects are important. Of course, I was forced to select a very small set of technologies to mention you, because the era is rapidly evolving, and many new technologies are adding in the landscape every time. And finally, in the processing, in the final analytics area, there is really the entire data science domain that it is really evolving into a brand new profession that can be pursued by those that are interested. So I'll stop now, and I thank everybody for the attention. Hope I was not too late, and I can take questions either online or offline, depending on the timing of the school. Thanks.
Thank you, Professor. It was a very interesting presentation. Thanks for your time. Do we have any questions from the crowd? The presentations will be also uploaded in our repository, and we will share the link to everyone. And so you can also have a direct contact with the professor for a collaborator matters or questions. So no questions. Don't feel shy.
I can maybe leave you my address on the chat.
Yeah, you can share your email address to the chat.
Okay. My address is...
Okay, if there are no any questions, we're going to have a break, 10 minutes break. So we will be back around 11:25 for the second part of today's session. Thank you. Thank you, Professor.
Thank you, everyone.
Hello. So we are back with the second part of today's session. During the second part, our speakers will present topics on machine learning, blockchain, and blockchain technology. We start the second part with Mrs. Nicoletta Prenzas, who is a PhD candidate on the Department of Computer Science located at the University of Cyprus. Nicoletta, when you are ready, feel free to start. Thank you.
Yeah, hi everyone, good morning. Thank you for the introduction. So today we'll start with an introduction to the area of explainable artificial intelligence with focus on explainable machine learning, and then I will present a hybrid approach towards this direction that resulted in the design and development of the argumentation framework, in short, Argumental. So we all know how artificial intelligence and machine learning is impacting our everyday lives, with applications ranging from digital assistants to medical AI systems. But despite its undeniable potential, for example, medical AI is not currently achieving this potential. And a major barrier for the adoption of these systems in clinical practice is the algorithm's inability to explain its results in a way that humans can understand. And therefore, explainability has become a critical requirement for AI and machine learning systems. Now, explainable AI is a broad domain that is being studied in several fields, including machine learning, human-computer interaction, and the social sciences. It refers to methods and techniques to make these systems transparent and produce results that can be understood by humans. The goal is to support the utilization of their predictions in the next task of the process and enable better or more informed decision-making. One of the major challenges in designing explainable models is the balance between accuracy and reproducibility. Of course, the quality of explanations is also important to build trust, And some researchers, for example, suggest that explanations need to be understandable, true to the model, and answer why questions. However, the most accurate explanations are not easily interpretable to people, and similarly, the most interpretable descriptions often do not provide predictive power. Furthermore, the Human in the Loop initiative suggests that for the successful application of explainable AI solutions in practice, we should combine the best of human intelligence with the best of machine intelligence. Based on a recent analysis of explainable AI works in the medical domain, in which physicians participated in the design and evaluation of the system, the results emphasize the need for an active role in the development cycle of the solution, and that comes in alignment with the human in the loop challenge. For a physician, after all, explanation is just another piece of information that needs to be examined and verified. And the physicians reported that explanations should be delivered to them in a visual interactive interface in a simple, comprehensive form. And they think of these ideal solutions to be, for them, conversation partners or expert companions. Now, explainable AI is trying to increase the transparency and interpretability of the machine learning model by explaining the decision-making process of the model to the user. For example, if you have a machine learning trained on histopathology images with a task to automatic detection of basal cell carcinoma, then the model will provide a prediction in the form this patient has a 0.96 probability of basal cell carcinoma cancer, and the explanation would be because of a particular reason in the image is abnormal. So to explain a prediction, we can use a post hoc technique that treats a model as a black box, occurs after the learning process, and uses the input data and the corresponding output to generate explanations to explain the model as a whole or a particular instance. We can also use anti-explainable techniques, which refer to either models interpretable by design or new or modified learning techniques. And we can also use hybrid techniques, which combine two or more different learning techniques. The explanation itself can be classified depending on the latitude scope of the explanation as global or local, with global meaning explaining the model as a whole, and local a particular instance of the model. Now, depending on the type of the explanation, this can be classified on as, for example, feature statistics, model internals, data points, and also based on the question the explanation answers, the explanation can be classified as attributive if it answers questions what or what by, as contrastive if it answers questions what if, and as actionable if it answers questions how. Now, a novel approach towards explainable AI is the integration of subsymbolic methods with logical methods of argumentation, a hybrid technique that combines the benefits of two different learning paradigms. We have experimented with this type of integration for the development of explainable symbolic argumentation theories. The integration combines the interoperability of symbolic AI approaches with the high efficiency and accuracy of the machine learning models. And the resulting argumentation theories offer explanations of the underlying reasons for coming up with a decision. We have tested our methodology using random forests for a classification problem in the medical domain, and in particular, the prediction of stroke or not. In particular, we have trained random forests, and from there we extracted decision rules in the form of if-then. And then we use these decision rules in the context of the Gorgias argumentation framework to develop an argumentation theory, which was the explainable model of this hybrid technique, which we can use to input a new set of case, of a patient case, let's say, and query this theory with questions like whether a patient could suffer from a stroke or not. And if a prediction is possible, that is, if a solution can be derived from the theory, the answer will be yes, and the solution found will be used for the explanation. That is, the line of reasoning that explains the decision-making process of the argumentation. Now, an important aspect of this solution is the concept of dilemmas. Using just the machine learning, the prediction could be either right or wrong. But in argumentation theory, we can run queries for all possible predictions. That is, we can ask for a patient if it's possible to suffer from stroke or remain or not, that is symptomatic. That is, we can explore all possible solutions and have both positive and false, true and false predictions for the particular case, with justifications for both answers. And that way we provide the domain expert with a tool to resolve these difficult cases, which we call dilemmas, and enable the domain expert to take more informed decisions. We have tested this methodology on real data using asymptomatic aortic stenosis and risk of stroke study with 1,054 observations. The results are really encouraging compared to a subproductive machine classifier with an accuracy of 74%. Here we need to clarify that while dilemmas are not true or false predictions, for the purposes of this comparison, we consider them as errors, that is, false predictions. But still, the results are encouraging. And the explanation that we can form from the decision path returned by the argumentation theory could be like this. Given an input for the particular patient, we can ask the argumentation theory whether the patient will remain asymptomatic, and if we can get the answer yes with a particular with a decision in the delta, okay, and we can use this delta to construct an explanation in the form this patient is asymptomatic, an explanation in natural language, which we can use to answer questions why or why not, and of course can be extended to answer what if questions. Now, the argumentation-based framework for explainable machine learning is an extension and generalization of this hybrid approach. It is a framework for explainable machine learning development. It is based on a novel approach to machine learning that integrates sub-symbolic methods with logical methods of argumentation to provide explainable solutions to learning problems. The methodology is based on incremental development, exploring different options at each stage of the learning process. The learning is guided by the coverage metric first and then the accuracy. And by relaxing the accuracy requirement, we make room for difficult cases to be addressed as dilemmas. And this is a high-level overview of the methodology. As you can see, the learning process is guided by metrics like coverage, explainability, and accuracy. And the results is evaluated again by a number of metrics, dilemmas, and accuracy. These are configurable, and while we develop this theory, we find out more metrics that could be implemented during the requirements or during the evaluation phase. While in development, we test and experiment the methodology using artificial and medical data sets. And as you can see, in the learning process, we use machine learning and feature selection techniques in conjunction with the Gorgias argumentation development theories framework. So this is the machine learning pipeline that we explained in the previous slide. As you can see now, the machine learning and argumentation theory development processes are more interactive than before. We have different learning strategies that we can use. For example, we can start from rules, from rule extraction as our initial findings, or we can start from feature selection techniques, like relation coefficient, information gain, etc. The goal is to end up with an explainable model which will be the argumentation theory, which we will be able to query with different questions and get answers with explanations. Yeah. So the expected results of this work, it's a novel theoretical framework for explainable machine learning. And these explainable machine learning tools to be released to the community together with a repository of test data, and a front application for exploiting a decision support system for medical diagnosis, and methodological guidelines for applying the proposed framework in any learning domain in the context of an AI system. Thank you.
Thank you, Nicoletta, for your presentation.
I don't know if you have any questions.
Any questions from the crowd?
Hi, I don't know if you can hear me.
Yeah, we
Yes,
can hear you well.
Hi, this is Paolo Fazzini speaking. Yes, I've got a question about, thank you very much for this very interesting seminar. My question is about retrieving rules, logic rules from the black box that is the neural network. I was wondering if there is some connection between some fuzzy logic-based techniques which also have rules that need to be determined in order to have a working system. I was wondering if, I don't know, you studied some connection between fuzzy logic in this path of pursuing a meaning in the way classification happens in neural network or in general machine learning?
Thank you for your question. We haven't experimented with any fuzzy logic algorithms. We are using a package, the entries package is implemented in R to extract rules from ensemble models like random forest, XGBoost, etc. But I believe there are available packages that can extract rules from neural networks as well, but I'm not aware of any of such a package right now to let you know.
Okay, thanks. I've got another question, which is a little bit tangential. I don't know if, because there was this theory put forward by Naftali Tishby of the University of Brain Sciences of Jerusalem, which was quite discussed a few years ago about how to understand why deep learning works so well using the bottleneck information principle and mutual information. That was more addressed to understand why deep learning works so well, despite the incredible number of parameters sometimes needed to build a neural network. I don't know if this is also part of your study or something completely outside.
No, this is not part of my study. My study is mainly this integration of machine learning with the argumentation theory, because the problem I'm trying to address is explainability, and this comes by nature in argumentation theories. But we are using machine learning to take advantage of this accuracy and these statistical methods for data analysis, actually. Because the argumentation theory, you need to define your knowledge base from scratch. It's like you need to define your requirements, let's say. With this integration, we are taking advantage of the availability of data and machine learning techniques to perform some feature analysis and understand which features and which rules, which conditions to use to develop argumentation theories which will be general at first to cover all data we have in the data set, and also be able to and also add then preferences, and this is the flexibility of the argumentation to deal with these difficult cases that a machine learning will potentially predict wrongly, let's say.
Thank you.
Thank you.
Thank you, Nicoletta.
Okay. Thank you.
Anyone else?
Yes, hello.
Hello.
I have raised the hand. I don't know if it's visible.
Yeah.
Dear Nicoletta, thank you for your presentation. Actually, my question is, we mostly see nowadays that many groups are racing towards higher classification, but what I found interesting is that you talked about relaxing accuracies to find more dilemmas. So could you please give briefly like some examples of how you are doing this? Is it empirical, doing different experiments and with lowering accuracies? How it's actually, how can you do this?
Yes, if for example we use if we train a random forest and we do a rule extraction, the rules will be extracted in a compact form with multiple conditions and to be as accurate as possible. This means that it's difficult to cover all cases in the data with a particular rule, and we will end up overfitting our model.
Therefore, I believe every time the rules are mostly based, let's say, on the type of data set you're using, right?
Yes, yes.
Yeah, okay.
So instead of having rules with multiple conditions from the beginning of the learning process, okay, we are trying to find discriminative features that uniquely characterize our data and discriminate our data. So we're trying to have general rules that characterize our data, okay, and preferences between rules, between arguments.
So you have a universal, let's say you have some universal base rules, and except from these you can prolong all of extend the rules based on the features that come up every time.
Yes, this is the first step of the process is this universal and general rules that cover the data as much as possible, and then we do refinement with these preferences.
Nice.
So this is what this is what we mean with relaxing accuracy. We are not trying to have accurate rules from the beginning. We are trying to have general rules, and while the process evolves, we are preferences and refinements to achieve accuracy as much as possible.
Yeah, thank you. Thank you very much.
Thank you as well.
Thank you, Georgia, and thank you, Nicoletta, for the presentation. We will move to the next presentation, which will be given by Mr. Marios Hagiaros, who is a researcher in the Science Research Center and a PhD candidate at the University of Cyprus.
Can you hear me?
Hello, Marios. Good morning. Yeah, we can hear you very well.
Okay. Thanks for the opportunity. Hello, my name is Marios Hagiaros. I am a PhD student and a research associate at Science Center of Excellence. And today I will present you the preliminary findings of my study on the field of virtual reality cognitive gaming based on brain-computer interfacing. So limb movement, gestures, communication, and social interaction are the most basic and primitive principles for the survival of human civilization. And this quality enables one to be served daily, to share emotions, expectations, and creative thoughts with other human beings. And therefore, people who are suffering from motor disabilities do not have the aforementioned options for interaction. So brain-computer interface is a promising means to furnish them autonomy with basic, simple, everyday things. So despite the many important breakthroughs in the PCI VR research, some issues still need to be resolved, such as long training sessions cause fatigue, and most research is done under favorable conditions of experimental environments, meaning the results are not real life and maybe are misleading. So VR gaming may could help. So I'm interested to research the triptych of virtual reality, PCI, and cognitive tasks. So brain-computer interface is a collaboration between the brain and a device that enables signals from the brain activity and can control prosthetic limbs or wheelchair. And also virtual reality is the use of computer technology to create simulated environments. And unlike the traditional user interfaces, VR places the user inside an experience. And instead of viewing a screen in front of them, users are immersed and able to interact with the 3D world. So BCI systems analyze electrical brain activity and the electrical activity of the brain through non-invasive methods are recorded by electrodes on the scalp, and signals are amplified and digitalized by processing strategies, and the relevant signal features are extracted, processed, and translated into commands that can control external devices or applications. It is important to understand about the cerebral cortex because in many times the electrode placement depends from the knowledge we have about the brain anatomy, and the cerebral cortex is partitioned into two hemispheres, in which every hemisphere is classified into 4 lobes, namely the parietal, occipital, frontal, and temporal lobes. The parietal lobe is in charge of numerous functions, for instance, spelling, objects, manipulations, perception, and spatial awareness. Conversely, the language, memory, recognizing faces, and generating emotions are the main functions of the temporal lobe. The frontal lobe involves organizing, social skills, planning, flexible thinking, problem solving, conscious movement, attention, and emotional and behavioral control. And finally, the occipital lobe is related to interpreting visual stimuli. According to the International 1020 system, the frontal, parietal, temporal, and occipital lobes can be denoted by the letters F, P, T, and O respectively, as you can see here in the figure. The central lobe is not included, and the letter C is utilized only for identification purposes. And the Z, 0, implies that an electrode is placed on the midline. Also, even numbers 2, 4, 6, 8 are utilized to indicate the right hemisphere's electrode positions, whereas left hemisphere electrode positions are denoted by the odd numbers 1, 3, 5, 7, etc. Students of neurosciences are often bombed with generalizations such as alpha mediation, beta alert, theta fog, or SMR cal, and those descriptions are both helpful and misleading, and they suggest that each frequency bandwidth is one-dimensional or independent. Frequency bandwidths are definitive parts of the whole raw EEG. So delta brain waves from 0 to 4 Hertz are the slowest, highest amplitude brain waves and are what we experience when we are asleep. Theta brain waves, 4 to 7 Hertz, associated with daydreaming, mediation, creative ideas, and alpha brain waves, 8 to 12 Hertz, are slower and larger and they are associated with a state of relaxation and represent the brain shifting into idle gear, waiting to respond when needed. If we close our eyes and begin picturing something peaceful, there is an increase in alpha brain waves. Beta brain waves, 15 to 30 hertz, are small, faster brain waves and associated with a state of mental, intellectual activity and outwardly focused concentration. And this is basically state of alertness. And finally, the gamma brain waves, more than 30 hertz, are the fastest and most subtle brain waves and modulate perception and consciousness. In this paradigm, the user tries to imagine movement of specific limbs, such as left and right hand or feet movements, to send a command. So moving a limb or even contracting a single muscle changes brain activity in the cortex, and preparation for the movement or imaging movement, also known as motor imagery, generates oscillations in the brain motor areas. The most influential frequency bands for motor imagery are the alpha and beta brain waves, and activity invoked by the left and right hand motor imagery is generated from the areas C3 and C4 of the brain, and the foot movement imagery is originated from CZ. Left and right foot movements are almost impossible to distinguish in EEG due to the fact that the corresponding cortical regions are extremely close, and the cortical areas must be large enough to produce detectable patterns in the background EEG. And the cortical areas of left and right hand and feet are large and distinguishable. Thus, the movement of those body limbs, the imagination, can be controlled by BCI applications. So motor imagery can be used extremely well in cases such as prosthetic limbs, control of left and right hand movement in people with no arms, and for motor rehabilitation in disabled people. In this study, we investigate the ability of individuals to activate commands for hand movements using the appropriate EEG patterns via brain-computer interface, and we performed preliminary experiments on 5 healthy young adults where they were asked after a cue on a computer screen to imagine moving their left or right hand depending on the cue without any movement or muscle activation. So with the appearance of the cross, the trial begins. Then left and right directional arrows appear on the participant, and depending on the arrow, the user has to imagine that he was moving his left or right hand. The training protocol was designed based on the GRAD BCI paradigm with the standard feedback of the directional arrows, and this scenario used as a first step to collect some training data, and those data will later be used to train a classifier for online use. In the next steps, the first step of the training consists the acquisition of the raw EEG in order to train a linear discriminant classifier to distinguish right and left imagined hand movements. And throughout the training session, the user has to perform the mental imagery of the corresponding hand based on the presented stimuli. For each hand, the user is stimulated visually screen action observation, and the training session was configured to acquire data in 20 trials or epochs per class for right hand and for left hand in a randomized order. And following the EEG acquisition, the artifacts removal was performed using the Butterworth filter, and the data we are then used to compute a common spatial pattern, a spatial filter that maximizes the difference between the signals of the two classes. And finally, the raw EG and the spatial filter were used to train a linear discriminant analysis classifier. Here you can see the accuracy with which the system correctly predicted the class imagined by each participant, and the average in test data that the system has not encountered again is around 67%. And in people who had very low results, it is probably due to the fact that they made a sudden movement that moved the cap with the electrodes, and the system stopped receiving quality EG signals, or they may not have taken the experiment process seriously. But of course, more participants are needed to be able to draw the right conclusions. In the next steps, the objective is to aim in cognitive tasks related to imagination, attention, memory, and image recall, and to be checked if there is a correlation, if participants with higher cognitive skills can be better in a BCI VR game based on motor imagery, to be checked if the cognitive skills increasing after repeating sessions with the cognitive tasks for a short period, and to be checked if the users who increase their cognitive skills also increase their motor imagery ability into the BCI VR game. So we are trying to have a two-way evolution of algorithms and to train people how to create the appropriate EEG patterns. Thanks for your attention. If you have any questions.
Thank you, Marios. Very interesting presentation. The things that we are science fiction a few years ago now are part of our reality. Very interesting, and it's really nice that this awesome job takes place also in Cyprus. What are your thoughts, Marios, on the metaverse and how the brain computing can help, let's say, the decisions that will happen in the metaverse?
I think in the future we
we cannot hear you.
You can't hear me? Hello?
Yes, we can hear you.
Hello?
I can hear.
Can everyone hear me?
Yes, we can hear you. Most probably Panagiotis is out of connection.
We cannot hear you very well.
Panagiotis, he is okay. Check your equipment.
Just try to reconnect.
Okay.
Okay, in the meantime, Mari, please proceed with your answer.
Okay. I think metaverse, it's a big innovation, but also we have to work a lot to achieve good results, because the EEG signals is extremely non-linear and unstationary signals, and the brain of every individual is different. So we have a lot of work to create algorithms and use machine learning techniques that can work fine for all of the people, for all of the population. But I think we have very good results in this stage, and if we are continuing to trying to increase our algorithms and increase the abilities of the people how to learn to create the appropriate EEG patterns, we can achieve a lot of things.
Thank you, Marius. That was my mistake before. I was the one that having a problem. Sorry.
Okay, no problem.
With my speaker, so sorry. And because I didn't listen, you answered the question from the chat. Marius?
Yes, I can answer again in the chat.
There's a question in the chat. Is that the one that you answered? If not, you can also see that and try to answer a bit quickly, please, because we have.
Okay, hi, thank you for the great presentation. I was wondering, here is a question. I was wondering which characteristics of the EM signal coming from the brain, average frequency, magnitude, dominant frequencies, and etc., are extracted as input for the classifier, and if the combination of these signals coming from different brain areas is significant. Yes, is significant. We have to select the right channels according to the international 1020 system. And in my study, the right channels to select is C3, C4, because they are responsible for the left and right hand movement. So is the target channels, and maybe we can choose channels near of that channels to create some spatial filters such as CSP or Laplacian to get all of the signal around that target electrodes and to have better results.
Thank you, Marius. Thank you, Marius. If anyone else have any other question, feel free to reach Marius directly. So now we will move to the last part of today's session in regards to blockchain applications. The talks will be given by Professor Claudio di Ciccio from the Department of Computer Science located at the Sapienza Università di Roma. Professor, feel free, when you are free, feel free to start your presentation. Thank you.
Hello there. So I hope you're all right. I just took a little bit to restore the environment.
No problem.
Okay, so I should be able to share the screen now. Let's check this out. Can you see the PowerPoint?
Yes.
Screen, great. So I think we can start off. As for timing, so I know I was late, but I would like to know more or less till when. So if I remember correctly, there will be 2 sessions and 40 minutes.
Basically, regards to timing, you can do the presentation around, let's say, 1 hour. Let's say, is that enough?
Yeah, sure. Okay, great. So I'll adapt concurrently. Yeah.
For both, parts,
yes.
in 1 hour.
All right, I'll have it done, so I can skip some, futile details here and there.
Okay.
All right then. So apologies again for the mixing up with the time offset, and besides, I'm happy to say that actually this could be part of the things we might speak about when talking about the blockchain. So in this talk, we will see basically 2 aspects, right? So first, we'll have a introduction to the very foundations of what the blockchain is about, to make sure that everyone is on the same track and we can talk freely about the research directions. that would then come as a second part. Maybe I'll cut loose here and there, but I'll focus on the topics that are most relevant to, talk about, hot topics that are emerging lately, or not so lately, actually. It's like kind of a few years we're going on with that. Right, so my name is Claudio, and the surname is Di Ciccio, for those who are wondering how to pronounce that odd surname with all these C's and I's, etc. It's as if it's written like TCH, so Ciccio. All right, so my background, I'm a computer science and engineer, and then I'm currently an assistant professor at the computer science department of Sapienza, as you may have seen at the very first slide of this deck. So why am I so interested about blockchains? Well, briefly, the main thing is I was always curious to know more from data, what was going behind them. So when we look at certain data, they're recorded by what? By a system typically. And how does the system behave? Well, typically systems enact processes, and I'm being curious in the research groups I've been proud to be part of, to retrieve information about the behavior of systems, processes, from the data that they leave around. Let it be from, let me see, I think you should be able to see a laser pointer, right? So it'd be from emails to logistics data, and ultimately from the blockchain, right? So because the blockchain, in fact, as far as we see it today, is a process enactment infrastructure. Wow, too many words at once. Never mind, we'll get through all of them little by little. So yeah, I said, like, been working in Sapienza in Rome for most of my time, and also spending 7 years at the VU Vienna, at the Vienna University of Economics and Business. Then I'm back now in Rome again. So to start off, for this talk, there are a few readings, at least for the first part, right, the introductory part, that you might find interesting. Now, we won't go through all of them one by one. Also, this meeting is being recorded as far as I see, so essentially you might watch these links later on. This one is, I find it particularly nice because it's very, it's kind of short, concise, but still has most of the core concepts we're gonna see today. And of course, the book from Chi-Wai Chu and others on architecture for blockchain applications is also quite an interesting one. Then, of course, the white papers, Nakamoto and Buterin, the yellow paper, which is called yellow because basically it's on yellow paper. That's really like it is. It's a bit more academic-like with the formalizations of the structure behind Ethereum. And then these are more like readable books, like this one from Dietrich. It's more like a novel, right? Really expresses what's behind Ethereum. And this one from Chris Dannon is also fairly interesting, although a bit outdated now because it's from 2018, if I'm not mistaken. So some concepts are a bit outdated now, but the core fundamentals are there. They're all there. Okay, so first off, when you see an asterisk here and there, it means that it's true-ish, okay? So some things about the blockchain are approximations. What does it mean? That technically the infrastructure is built in order to have it guaranteed up to a statistical percentage, which is usually very high, but it's not like fully certain. What do I mean by that? So for instance, transactions are immutable. Yeah, it's true to a certain extent, unless there are very improbable attacks that make it such that there is a conquering of most of the network, etc., etc. Never mind. For now, let's see. There is this nice definition from Yancidi Lakhani in 2017, who said the blockchain is an open, distributed ledger that can record transactions between two or more parties efficiently, yeah, kind of, and in a verifiable and permanent way. So we'll see what distributed ledger means, what ledger means in the first place, what is a transaction, what are the parties involved, and so forth. So blockchain in a nutshell is way more than just Bitcoin, okay? So it's a lot more behind it. So what does it mean? The potential is still largely unexpressed. Still today, it's 2021, we're getting through the maturity of the blockchain, and still many of us confound the blockchain with a mere e-cash system. In fact, it's not. It's more of an infrastructure. It's a paradigm shift to some extent for the execution of systems. Some people may have made a paragon between the blockchain and the internet. In fact, it's not too appropriate, at least this is my opinion in that, because actually the blockchain works because we have the internet. So it's a sort of a part of project. So what we can see similarly, though, is the unexpressed potential. So at the beginning, the internet was pretty much this, right? So I purposely use an old-fashioned looking browser to show one of the very first pages we had in HTML. So actually, this system is the basis with which you're now watching this very seminar or talk remotely from home with your browser, perhaps, yeah? So that's precisely the same system. Would you have place your bet about this? Well, back then, maybe not, but nowadays, here we go. Likewise, with the blockchain, we're still at the kind of, we're getting to the mature system, but still there is a number of things to be done by hand and a lot to study to make it work. So we'll see the explosion in the next few years. That's a prediction, not only as a cryptocurrency system, but also as a process enactment infrastructure. So some people also talk about, well, some people, especially the blockchainhub.net people looking in Central Europe, speak of the blockchain as the blockchain enhanced internet as Web 3.0. Why? So Web 1.0 was the one at the beginning of the story, which we basically have a client and server paradigm. Client-server paradigm with a front end and the back end. So here comes the server part, which serves pages, information, basically, from the server with its own databases, more than one perhaps, to the clients, which could be, like old-fashioned browsers here, like Netscape, Internet Explorer, but also some applications that don't have an HTML reader, but directly work with information exchanged on the web. So the client sends a request, the server answers. And typically these are thin clients, okay? So they don't do much on their side. Most of the computation happens here. With Web 2.0, which is pretty much the platform you're using now for watching this very seminar, we have, computationally more power for clients, right? So nowadays, Google Chrome could do a lot with JavaScript, essentially, even running remote applications, including maybe the web interface of Zoom now, if you're using that. Zoom itself is also connecting to the web for this. And yeah, so what we can say is that typically we now have applications that have not most, but a large part of the computation in the front end, which have dramatically changed as the good old click and go paradigm is nowadays fairly abandoned to some extent, right? So you just see the interface, which doesn't really change if you're using a standalone or a web application. You actually don't distinguish it. So the Web 2.0 was essentially a large change, but in the front end more than the back end. With the blockchain, with the inclusion of the blockchain in the recipe, well, the change now happens mostly in the back end. So it could technically be that the changes are not visible to the clients. The clients, in essence, are still perhaps using a mishmash of JavaScript, perhaps HTML, CSS, if you like, these old-fashioned web paradigms, except they don't connect directly to a web server, perhaps, but they interact with things called smart contracts, which are programs that run on chain. Repeat that. Smart contracts are not necessarily contracts between parties who have to sign and strike a deal, but they're basically programs running on chain. Okay. So let's go through the blockchain in a few slides. So the first concept we saw in the slide from Yanciti and Lachani was, well, with a quote from them, was that we have transactions. A transaction merely can be seen as a sort of a check, right? So, a check, this thing that you typically sign, you get a booklet from your bank, and you can use these guys as a sort of a transaction confirmation from A to B. So they are equipped with an ID. there is a sender, right? This Miss Jones here. There is a recipient, so who's gonna get the what? Well, the amount of money we're sending around, yeah? And it has a signature, plus a timestamp, so which refers to when the check was signed, typically, or when you want actually the check to take effect. And then the message, which typically motivates why we're sending this money, yeah, from bank account A to bank account B. Now, transactions for for blockchains are nothing so different after all. So you can still see that there are accounts here. We call them externally owned accounts, EOA. Yeah. So there is a from and a to, and there is a digital signature. So what we don't sign on paper, we sign digitally, still making sure that it's us with a two-way encryption. And then we basically transmit value. So look at here, there is a little animation. So we have an amount of assets here that get transferred to the other side, and the value is specified here. Plus, there is also this message field, which for now I kept intentionally empty, but it could be here. All right, we'll see later on how to make use of it in a kind of uncommon way. So this is it, pretty much. This is a transaction, right? So transaction is transmission of value from A to B. So what is the ledger then? Well, the ledger is something, it's a fairly old English term that refers to these books where you take notes of all the transfers of assets from A to B, well, from client from one to another. So these are called ledgers, that's it. The ledger has something very important in it, yeah? The thing being very important is that you must make sure that the transactions are sorted out precisely. So aside from the timestamp, we might have to make sure that what happens first is first in the list, and what happens after is after in the list, appears after in the list. Why is that? I'm not sure if we have time to delve deeper into it, and there's a sort of very quick example. But the main thing is we want to avoid the so-called double spending. What do you mean by that? Let's consider now we have account A, account B, and account C. We talk about accounts, okay? So it could be perfectly be that the accounts A and B belong to the same person. Yeah? So one person, another person owns C. So this is a timeline of the existence. Yeah? Now, in yellow, the first transition. So let's imagine that A starts with 100 buckets, and this guy has 200 buckets. Well, let's not use the dollar sign. It could be misleading. Let's use kind of this guy invented, like his coins. And C has, I don't know, 50 coins. Now, B wants to have a service from C, and this service is worth 120 coins. So B sends a transaction to C of 120 coins, right? C is happy with the payment then. So when we come here, what happens is we have then 80 left on this side, and now here we have 170. In exchange for that, B, watch out, off chain, sends something, let it be a service or a digital asset, music streamed live, video streamed live, whatever you like, to C, okay, to B. And then B tries to send another transaction, say of 100 coins to A. Now, at this stage, the system would then refuse this request. Why is that? Because essentially, we only have 80 buckets in our account, we can't send 100, right? So this is one of the few controls would basically any decent cash system would do, right? So then, what I mean is, but watch out, it's fairly important. This part here, so the part above, this guy, happens off-chain, all right? I told you, off-chain. So if we have a decent ledger, then we would have that transaction, say transaction X occurs first and transaction Y happens after and actually is refused. Okay. Now, what if we could kind of take over the system and convince the community that in fact, after some time, right? Not immediately. So after we received our service, we convinced the community that instead reality was different. That we first sent the 80, so first Y with 100 coins from B to A, and only then we try to send X with 120 coins from B to C. What would happen there? Well, essentially here we would have a drastic decrease to 100 coins here, and here would be 200. Later on, then the X transaction would be, sorry, it's written very badly. Let me try again. Okay, now it's more comprehensible. Then the same transaction here would be refused. But as we took over the system after we received a splendid, magnificent service, this guy, which happened off-chain, will still happen. What then? Essentially, the owner of the accounts from A and B would still be happy because all in all, the amount still remains of money they had at the beginning. It stays the same. So it's all in all $300, right? Exchange between B and A. C would not have anything more than the $50 it had at the beginning, except C has offered the service to B for free, right? So for once, definitely this is what we don't want. So we have to avoid this part. So to avoid that, typically in transactions is correct. Well, I can tell you the other transactions is correct because there is a bank. Yeah. If it's not a bank, it's either a credit institute or a creditor, or, you know, in the old days, someone who's liable for this. Okay, so the one who writes the ledger basically is the one who guarantees that the ledger reports the right transactions order. So as a paradox, actually, what would happen is that back then, if you could bribe the one who wrote the ledger, you would basically take control and then decide whatever you like that happened, right? So this, again, something we don't want for a fully autonomous system. So we'll see later on how to avoid that. For now, though, you know, if you had a very, very long ledger, one book is not enough, right? So you have to start, you know, abandoning a notebook and opening a new one and start writing the ledger down. Now, thing is, in systems like that, you might have the same metaphor. And again, you don't, well, just a chunk of a ledger is not enough. So you start, you know, slicing the ledger into things that are called books any longer, but blocks, okay? So we call them blocks. Now, there is something very important. When you have a notebook and you pass on to the other one, you have to remember which was the preceding notebook, right? So every notebook should refer to the preceding one in order to remember what is the right order again. Nothing different with the blocks. Okay, so every block refers to the preceding one, and then it creates a chain. So a chain of blocks, blockchain, ta-da, there we go. The blockchain then remembers everything that happens in the blockchain stays in the blockchain virtually forever. So what we said before was we want to avoid that if you bribe the bank, the banker, the creditor, whoever, then you can manipulate the ledger. This can happen if you have a central authority that governs it all. And I'm not saying not necessarily it's bribing, it's also about attacks. If you were able to attack a credit system and you start manipulating the contents, well, you can become fairly rich out of it. There have been cases in which there have been extremely good hackers who hacked the system and started, you know, subtracting a little amount from every transaction, very little amount, like a lot of thousands of dollars, still becoming rich out of that. Then they got caught for other reason, but then anyway, they could do that. So because basically there was one point attack. Now, the blockchain approach is instead different in that, well, blockchains, but also distributed ledgers in general. Here comes a distributed term. So it's not enough you attack one, they call it node. You can't just attack one node and hope you'll make it. In fact, there is a copy of a ledger in every single node that is connected to the network. All right, so the ledger is distributed. Therefore, we can say that every node sees as if it's a central mechanism, right? So every node virtually thinks that the ledger is, in their own hands, more or less as if we had standalone applications having a replica, the exact replica of the whole database. Let me call that database for their own. Now, as pretty much always, when you have a tremendous advantage, which looks like, wow, that's groundbreaking, that solves the whole thing, right? You can't just attack one node, you have to attack all of them to make sure that you got your reality manipulated. There is a fee to pay there. The fee being, if you want to keep this system consistent, you have to send around notifications of updates all over the place. But still, we are in a physical environment in which we operate with bits and bytes, and it's transmitted over a best effort distribution broadcasting system, which is the internet. So you can't have the guarantee that every node sees exactly the same replica in real time of the ledger. So there are a bit of discrepancies. Also, and we experienced that live, not all the system could think of the timestamp the same, right? So what was noon in Cyprus was, to me, as I think you can see up here in the screen, it was 11 a.m. and I thought actually the conversion was 1 p.m. So my bad. So this happens also not only to humans, but also to machines. And this could be a reason why we can't really take into account as a reality checker the timestamp of blocks to sort out transactions and blocks. By the way, if I hadn't said that before, let me say that the units with which there are communications being sent around is, hold on, should work now? No. All right. So that time a new transaction happens, it's basically parcelized, so and wrapped into blocks that are sent around. So I hope things are fine. You can still listen to me and watch me. If there are any issues, I hope not, because the Zoom system just told me that my internet connection is unstable. I hope not.
It's okay now, it's okay.
It's okay, fine, great. So as I said, well, the instability of the network is also, it's interesting. We are having a lecture in the lecture live. So instability of the web could also be a cause why updates are not so reliable. Likewise. So indeed, the distributed nature makes it such that the chain of blocks could be of one kind on one node, of the same kind on other nodes, but could be different around. So look at here there is a chain of blocks, another chain of blocks, another chain of blocks, but here, for instance, the latest block is not there. Maybe because the internet connection is low and it has not yet reached the destination. Like the gossiping the broadcast has not reached yet this node here. So there could be, suffixes that are unknown, or also there could be different views. Oh, sorry, actually, this is the missing suffix. Here, actually, it's a different story. Here, there is a block which was appended to the preceding ones, although it's not known by the rest of the net. So there is an inconsistency, right? So the latest block here is yellow, here it's purple, so something could happen. So as said, just a recap, centralized is when you have one source of information. Decentralized is an architecture in which we have a number of nodes think that actually the center of the information is themselves, and decentralized is when instead we have information spread all around. So architecturally, the blockchain resorts to a distributed ledger, which means that the information is distributed across nodes, but in fact, there is a decentralized conceptual view because every center of information thinks that they are the service of this information, and also there could be light nodes plus not all the nodes are entitled to send blocks around. Let me repeat that. It's not that every node can invent, here comes a new node, new block. You all take this into account and update your block, your chain accordingly. Not at all. This would be too naive. There would be too many different folks, they call it, too many different views on the same chain. Because if everyone says, what's the next block? Well, this wouldn't work very well. So what happens then is that we have to provide a way to kind of not guarantee, but at least give some intuition that at least the ones who publish the block are ones who can be trusted to a certain extent. So what's the way? I'm not sure we can deal too much deep dive into this topic, but essentially the idea is not all nodes can publish new blocks, but only some of them. And to decide who they are, there are a number of algorithms. Typically, these algorithms are based on a system that should guarantee that kind of, not guarantee, but work towards the fact that the ones who do publish are really interested in keeping the infrastructure up. So it's not for malicious intent. The first, among the first ideas that came up with Bitcoin, for instance, was the proof of work. Roughly speaking, proof of work means you node before publishing the block, you should try to solve a puzzle. Well, not actually, to do a right guess for a numeric puzzle. And if you guess the right number, so you solve this puzzle, then you have the right to publish the block. Notice that this mechanism is very hard. So typically solving this puzzle is impossible. You don't solve it, you just guess what the solution could be. And after a very wide number of attempts, if you're lucky enough, you can publish the block. This is the proof of work. So if you work long enough and you're lucky enough, you can publish the block. Now the thing is, this is a competition. So there could be very many nodes trying to do the same thing at once together. So that's why it's a race, it's a competition, and therefore many are required to participate. Now you can see that if we set up a competition and we start up such a thing, there could be a prize, a reward, right? Well, this reward is essentially, here's the first time we talk about currencies, right? Some cryptocurrency out of the blue, right? So if you guess the right word, you publish a block and this block is accepted by the rest of the net, well then you get some freshly minted cryptos, okay? This is called mining process, exactly because as miners, you find gold out of nothing where there was a cave or some water flowing. Here, same story. You got some cryptos out of nothing. So essentially, the currencies, such as Bitcoin, for instance, are sort of crypto fuel. In order to make such that most of the nodes at least behave, well, the vast majority works in a way that doesn't, that is not malicious, but actually it's worth the effort, we have to pay them back somehow. If for nothing else, at least for the timing spent and the energy being consumed, right? So after all, the electricity bill would come over. So the crazy thing start, well, this the screenshot is fairly old. You can see like Bitcoin only worth 5,000 euros. Well, very old, very interesting. Oh, come on, this is the column, 7,000. Anyway, old-fashioned. Nowadays, it's at least doubling, tripling, fourthling, whatever the amount. Okay, so anyway, the idea was to start, putting on the market an exchange, so you can have cryptos not only by mining but also by buying them in fiat currency, and this paves the path towards the usage we have seen so far as of cryptos as a kind of real currency, which is recognized as a method of payment. So this is today, not really today, sorry for not being very updated, but it's like $56,000 a Bitcoin. I think it's a bit less, but anyway, nowadays we're getting towards those amounts. Not only that, we said in the beginning slide that it's we're dealing with an open protocol. Open means that you can take it, manipulate it, and make a new version thereof. That's why we have a number of alternative coins. It's an incredible number. So remember that we have, with signing, we have pseudonymity, another ingredient in the pot here. When we talk about at least open public blockchains, what we have is that you have accounts, but people may not know who these accounts belong to. That's why in the example here we said A and B are accounts, but we may not know that they belong to the same person. Same story here. There's a sort of secret for the banks, for the account. Sorry, everyone knows what's the account number, who's doing the transaction, because the ledger is in every node, so everyone knows who sent what to whom. We just don't know who's who, right? So we just know there is a number, an account number. That's it. So there is a pseudonymity. And to guarantee that, then there is a signature that takes into account only, sorry for the word joke, it's unintended, the account number of the sender and the content of the transaction. To sign, you need a private key that only the real owner has, hence the need for wallets. The wallets, if you have heard the term, typically store your accounts and the private keys that you have for yourself. And if you lose this private key, well, that's it, goodbye. There is no bank you can resort to, because there is no bank at all to whom you could ask, to which you could ask, sorry, what was my private key again? No way. If it's lost, it's over. And the public key, which everyone can verify to certify, yeah, the signature is yours. Let's skip this. I think it's not really needed for the intents and purposes of our lecture today, also because we're running out of time. And another key ingredient here, aside from private public key cryptography, public private signatures, is hashing. So very briefly, hashing is a way, is a function that takes a digital input. By digital, I mean made of digits, so numeric input in. We're talking about computers here, so everything can be typically a number. So message in, and returns another number, which is called digest out. No secret keys here, okay? So for cryptography-enabled signatures, you need a secret key, but for hashing, you don't want it. No secret key at all. All operations are public, again, all right? So how does it work? It tends to create digests which are kind of unpredictable, yet deterministic from messages. What do I mean by that? So if I try to use SHA-3 with 256-bit outputs, so a digest made of 256 bits is the output. As an input, I take hi there, we have this output here. It's kind of unpredictable. If we try to submit a similarly semantically connected message, such as hello there, well, the number is totally different. We have no way to understand what's the relationship between the two. But watch out, one might say, hey, okay, right, but hi and hello, we know they have a similar meaning, but because we are humans, let's try with something which is similar in terms of Levenshtein distance. So let's try typing blockchain with an uppercase B and with a lowercase b. Again, the distance here is just, in place of an uppercase B, we use a lowercase b, but still the numbers are totally different. Again, just we can make sure though that this is deterministic, meaning that if we submit blockchain as a string to this function here, we always get the same output. Just it's terribly difficult to by terribly difficult, I could claim almost impossible, although nowadays there are quantum computers coming over, but anyway, so it's very, very hard to reverse engineer what was the input given the output. All right. So if you want to try this out, why not go into this link and see what happens with the hashing? So all these examples would be explained. So the timestamping system with the blockchain works with the hashing. So the chain link is given by getting the block, hashing it, putting the hash of the current block plus include the hash of the previous blocks together so that you can't really do anything with them. If you try, so you can't really tamper with history. Tamper. It's a term you might have heard in the past referring to the blockchain. It means manipulating. So if you try to manipulate this block, yeah, then the hash will change in a way you don't possibly know. And if you include, yeah, in the soup also the hash of a previous block together with the hash of a current block, and you create a hash overall out of it, then you can't really change the previous block without having an effect on the hash that you're transmitting to the next block. That's a system, that's a link, right? So more precisely, we take into account the headers, but nevertheless, that's the idea. So the very first block is called Genesis block. So the nonce here is used as a secret ingredient for the proof of work. So ideally what happens at the, well, we will skip through this, but just to give an idea, the proof of work system works like that. It's kind of trying to do the impossible. I tell you what's the expected output, or at least what's the expected part of digest they want. And you have to include in the block header a magic number called nonce. You have to guess in order to have that the output starts with a given amount of zeros. So if, for instance, let's do a very smart simplification, like saying, well, we don't take into account the whole block, we just take a string, yeah, and want to append the nonce to it so that the short by the way, here we're talking about hexadecimal zeros, okay? So hexadecimal zeros means that they are like 4 times this amount. So it's 6, 4 times 4, 20, 6 and 4, 6, 24, then bits like zeros. So you can guess the right amount with this number here only after attempting brute force 10 million and counting almost 11 million attempts. If we add another 4 zeros on ahead, then we can see that the situation gets even worse. So we need 934 million attempts to get it done. It's huge. Now, however, again, you can try yourself. A few links here. A smart idea could be, well, you know what, because we know already what's the characteristic of a number that we have to, you know, return. Well, then what we can do is that we know the amount of bits that the digest has. It's written here, 256. So what to do then? Well, let's try and divide the ranges of numbers that we can possibly put here in order to have the leading leading bits being 0. Yeah, we then give a slice of attempts to a machine. Another machine would take another chance, another chance, another chance. That's why we have this called mining rigs. That's what they do. They try to infer what's the right nonce, this little number put here, to solve the puzzle in farms, basically, right? So there are in parallel many machines working. All right. So in Ethereum, as opposed to a Bitcoin, in order to avoid the use of ASICs, they have been using also another additional thing that basically clogs the random access memory, so the primary memory of machines. ASICs don't have big memory attached. That's why they don't cost too much. But if you have to, you know, store a gigabyte of data set every time you run this algorithm, then should avoid that. But this is not actually one of the most brilliant, no, it is brilliant, but it's perhaps not one of the most well-known updates that the Ethereum supported. The first being that we have smart contracts. Smart contracts are super clever because, well, not because they are contracts, not because they're humans. They're in fact smart because they are kind of encoded, and they're called contracts because of historical reasons. But in fact, if you, I don't know how familiar you are with programming, but if you look at this code here, it tremendously resembles some sort of Java or object-oriented JavaScript, if you like, also object-oriented Python, if you prefer, but it's more like Java-ish thing. Anyway, nothing more than that. So it's just a class, if you want to call it like that, which, however, lives on-chain. So in the blockchain ecosystem, you can't run it outside. It only operates and lives and takes information within the blockchain. Now, what does it mean that it lives in there? Because it means that we have a distributed nature, so we basically run the contracts on every node. So every node that belongs to Ethereum, virtually, every node that belongs to the Ethereum network runs the contracts. Now you might wonder, okay, I see. So you have transactions on one hand, and on the other hand, you have contracts, which, okay, I got it. Yeah, they're classes, like they're running on chain with, I guess, something virtual machine like Java. Yes, indeed, you got it right. It's Ethereum virtual machine in that case, it's called. Yeah, but how to merge these two concepts? Well, it's kind of intriguing. And here comes the piggybacking I mentioned before. So imagine this. In the message field of your check, you don't have a writing any longer about the motivation why you're sending the check, the amount, but you have some encoded information. What does it mean? So if you want to invoke an existing smart contract function, you assume that there is a smart contract owning an account. Yeah. So they're kind of independent in this way. They're programs. That's why they're so cute, interesting, and also kind of dangerous, if you like. There is not a human or a bot or any agent controlling the account, but actually the piece of code you put in, that's managing the account. That's called smart contract account. So to invoke a method of, or a function, if you like, of a smart contract, then you submit in the payload an encoding of the invocation. Really not joking, that's what happens. So you can have input, output, encoded data, and but you also have to do something else. In the blockchain, typically, because of the crypto economic incentives, there is a cost to pretty much everything. So if you want to submit a transaction, there's a transaction fee, which we didn't speak about in this class in the interest of time. But to execute contracts, you need to pay something, and this is called gas price. Again, crypto fuel at work, right? So why is that? Well, remember that we said that the smart contracts are being executed in every node. Okay, so the best way to attack and tear down the whole system would be to try to, submit some incredibly complicated functions, perhaps never terminate, never end, and you invoke them on purpose. So what happens? It's kind of sort of DOS attack, isn't it? Well, then the answer to this from the Ethereum guys was, well, try that. If you want to run a function that never ends, you have to pay an amount of money that never ends, right? So it's an immensely big amount of money. So that's why every operation, like the low-level operation, kind of assembly-like operation, has a price. This is called gas price. So are we impeding systems to attack to run a DOS or whatever? No, well, technically no, but practically yes, we do, because it would cost an infinite amount of money. Now, what's even curious is, okay, so if we assume that there is already an account with a smart contract attached, all this kind of makes sense, or at least I hope so, right? But one question I often receive while during this class is, okay, but then how do you deploy, to use a Java-like term, or an enterprise environment term? How do you deploy smart contracts? Well, this is even curious. We don't ever get out of metaphor. Again, the transaction is all here. We submit a transaction to a new address, which is not occupied yet. Yeah, and the code of the contract is again in the payload. And then, poof, all of a sudden, we'll have a new smart contract account with a smart contract whose code is attached as a payload in the new address. So all of this constitutes what I said before, the Ethereum virtual machine, which is a sort of globally accessible machine that pretty much all clients go to input their data and get some output out of it. And as said, there is an assembly code which is being used. You can use also high-level coding languages such as Solidity, an example of which we saw a few slides ago. And all of the operations at low level have a gas amount. So depending on the kind of low-level operation the smart contract operates, we have a different cost. Yeah, so it comes with, at no surprise, I believe, that the storage writing operations are more costly, whereas the reading ones are less costly. Yeah, and the mathematical arithmetical operations are typically the least costly ones. Mind that gas is not ether. The reason being that we want to give a sort of second tier exchange. So you have ethers can be exchanged for fiat currencies, dollars, euros, but gas price is defined in terms of ether. Okay, so you can tell actually as a client if you want the miners to give priority to your request to promise a higher gas price. So you're saying, you know what, I'm incredibly wealthy, and because I want my invocation to be executed first, dear miner, I'm ready to pay more. I say dear miner because the miners are the ones who decide what other transactions to be included in the block and then gossip them, right? So this sort of official legal bribing, so to speak. Dear miner, if you allow my request of function execution on a contract to be run first, well, I'll pay for the gas more in terms of ether. All right, let's go ahead. So the key interesting thing is that then if we consider the contracts as classes, then the whole set of contracts and accounts in general, they are all there, constitute a big machine, which has, as every machine, a state. Well, as every stateful machine. Yeah. So I know how many of you in the audience are technology or computer science savvy, but think of it as an incredibly big system with a finite number of states. Well, virtually infinite because we're getting to it's not meant to terminate anyway. So there are a lot of to another is dictated either by payments, so transactions from A to B, which changes the state in the sense that we had an account having, I don't know, 100 ether, another one having 0 ether, then it gets to 99.1. It's a change of state. Or the state is mediated by the invocation of functions, methods on contracts. So contracts kind of delimit the amount of possible changes of a state. All right. So remember that the execution of contracts is typically or ideally on every single node. So first on the mining nodes, because they have to, guarantee that transactions can be included in the block and then gossip them, but then every node. So what happens on one machine happens on all machines. What happens on one node happens on all nodes. Pretty much like, typographic machines like the one you see here on the right-hand side. So only remember that for your own sake, only the code that is absolutely needed to be executed on chain shall be written in Solidity or any language you like. So the block rewards are incentives for miners. Take into account that perhaps pretty soon there could be the so-called difficulty bomb. So when we say, all right, let's stop this proof of work craze, from now on, there wouldn't be any new incentive from the mining. It will be only from transaction fees, gas execution, and the like. So we can create tokens with a few lines of code like this. In this case, a token is something slightly different than the currency because the tokens are essentially numbers stored by a contract, which sounds crazy, but that's the way it is. All right, so a token is then backed by a contract. So a contract can be typically a token. They can be called the same. So there is a difference between a typical cryptocurrency, such as Ethereum or Ether, actually, Bitcoin, algos, as opposed to tokens. Tokens are programmed like contracts, and they managed with balances that are nothing else but dictionaries mapping addresses, so account addresses, to a number. And the other number is how many tokens you have. And if you're smart enough, you can include a terminate function that when the contract goes off, sends all the properties of the contract to the original owner. That's the way to make a fairly good amount of money out of it. Then all the rest is basically creating, it's not too difficult, to create a web interface for this contract, and then you have your brand new token in 5 minutes or less. We have a few examples of when things got out of control, but I think we can skip that part. So remember that this is the most simplistic part to treat the blockchain. No, this is the burst model. It's a sarcastic example. In fact, you may need a blockchain in those cases in which you have multiple participants that don't trust each other, and you need to write information that everyone must know. Okay. Then the model of burst and JRA has a kind of additional layer, which means, do we want to create blockchains that are fully public, or do we prefer to use public but permissioned or private permission blockchains, meaning can everyone access public-private the chain? Can everyone determine that they are the miners? Permissioned means that the competition is open to everyone. Permissioned means that the miners are not all the nodes, but a part of them. Also from Kunz and Paul, etc. Now, sorry for skipping straight ahead to the next part, but in the interest of time, I would just get there. If there are any questions, I may not have been able to read them because I can't see the chat, but in case, please feel free to interrupt me anytime. I hope the basic concept were understandable enough. And yeah, let's then get to the next part, which would be some open research directions. During this first part, I think we had a look at the core fundamental parts thereof. Let me check. I should be already open. No. Sorry for the loss of times.
No problem. Is there any question, guys? No questions, so we will.
All right. So no questions, then it means we're getting ahead to the next part.
Yes, yes.
All right. So a few research directions on blockchain and processes. Yeah. So I told you I'm a process guy. So I like to see things in an organized movement, so to speak. So it's a fairly old concept, which was dating back to the Industrial Revolution, in which we so in this case, Mr. Smith, the famous Adam Smith, yeah, this guy, who got that typically you could divide work in subunits. And this is something that to computer scientists is very well known as modularization, yeah? So you modularize your software to let small problems being solved by small units of work, and then altogether that you can create complex structures that, like the workflow, yeah? The workflow or the application consists of invoking many functions and then all together in different orders until you get your final result. Same thing happens for division of labor. Now, might sound a bit inhuman, but nowadays with machines that sounds pretty cool, good, right? So because we can create, IoT systems and Internet of Things with sensor actuators and organize more complex appliances to make them such that pretty much humans are aided by machines in the conduction of the work, leaving typically the routine to the machines. We're very happy to do always the same thing, as opposed to humans who typically like to do things a bit more, different time over time, just not to predict that the everyday is always the same, right? So that's a kind of human-aided operations. Machines like to do always the same thing, like to be encoded. Well, I don't know if they really like that, but I never asked them, or at least they never answered. So We assume that. Also, the systems of machines like to report on a job. If they're fairly well programmed, they log what they do. In fact, the ledger is a sort of incredibly long log, right, in which all transactions are logged, all the exchanges of assets are sent around. So in a tabular form, an event log looks like that. So in which we say basically what is the task name. You can identify that with the function being called, yeah, given a run, yeah, because we could run the same application multiple times, so every application run would have an ID, and potentially some sort of timestamp, which we don't really need, as long as we have a ordering of activities. What happens first, what happened later on, plus additional data. Now, typically, what we have when we speak of real data, it's not that tidy, but nevertheless, we can kind of hope we can return from fairly, untidy data to the original format, or actually to a tidy format, such as the one of the XES, which is a standard format for what I told you at the beginning was my favorite field of applications, which is mining, yeah, process mining. So if we have all this data, we can run analytics on top of them, looking at, for instance, what is the performance of our application. Or here you can read some German, because back then when I created this slide, we were working in Austria. So yeah, we can run this kind of analysis to check what is the bottleneck typically in the run of our processes, but also we can try to detect from the data we leave what are the behaviors of the interactions. So the behavior, we know already what's the behavior of our application. Come on, we encoded it, so we could run some model checking on top of those contracts to detect what's the intended or unintended behavior, maybe. But when there are users interacting with these applications, then we can't predict what users will do. So we might want to know what they're doing with our application, right? Because typically the unintended unintended or unexpected operations with our applications are the secret to breach. Also, we can check, not only discover, but also check if the behavior of the interactions are in compliance with the expected behavior. It's called conformance checking. And ultimately, change the applications to make them such that they have fewer bottlenecks, they have fewer unexpected behaviors, and so forth. This is process mining, guys, in a few words. Now, what does the blockchain have to do with all this? Well, we understood that we can basically encode workflows. This is a workflow on steroids with special logos for operations. But never mind, if you don't know BPMN, you can still get that the boxes are operations and the circles are events, things that happen at some stage, and messages are exchanged from one pool to another, pretty much like in UML. Now, we can turn workflows into code, but if we can turn workflows into code, and those of you who have been into software engineering know that you can do that. If you can turn executable workflow models into code, then we can also turn into code that is executed on chain. So there are a number of programs that do that for us, such as Caterpillar, Rollikit, and more are coming actually. Also Core4Chain. The research challenge is open. It's fairly recently new. Like the things started in 2016, 17, and are still ongoing because they, of course, they can be improved. And but if we have then programs that run on chain, we know that everything that happens on chain is stored as transactions. So they are on ledgers, and transactions are sorted and ordered. So that's why we can easily make a leap and consider ledger as a huge event log. So, and if we have event logs, we can run process mining atop. So in the end, we can kind of check the conformance, enhance, and discover the usage behaviors out of the event logs that report from the blockchain. That's the intuition. How to do that? Well, There is a little bit of handwork there, which is maybe not so intuitive, but of course, this is manual because it was a research prototype. Nowadays, there are more and more applications being developed that are, in fact, automatizing all this. Even startups are now coming over to turn automatically blockchain events into logs. Back then, though, it was a bit more of a challenge because we had to look into the contracts, look at the so-called invocation header here, which basically is the SHA-3 of the name of a function as per the application interface. So if we know receive order, we hash it with SHA-3. The first 2, 4, 6, 8 times 4, 32 bits are encoded. They're always the same. So so we know that receive order is in the payload of the transaction data because the first 32 bits are the first 32 bits of the SHA-3 encoding of the function name, right? And then also the parameters are passed, they're appended to it. So then we understand what are the contracts that they're routed to. We check, basically repeat that part for all the possible invocations, intercept invocations, detect which are the actors operating in the transaction, and then turn them into XCS logs. To do what? So basically having the activity label being the reverse engineered function selector, the event ID being transaction hash, the case ID being transaction 2, so the contract basically detects what's the ID of the run of a program. The resource operating, we can assume it's the from field of the transaction. We can even consider the cost of invocation, which is the gas being spent. You know, all of this. And then we have the event log, fresh event log, from which we can run happily process mining toolkits atop. Of course, this is the first step. Then we could consider new tailored systems that do this, not in general for processes, but specifically for blockchain-based applications. Why is that? Because once we have these conformance checking algorithms, for instance, running on top of a chain, we can create some sort of systems patrolling, like sentinels, what's happening on chain, trying to detect on the go if there are certain unintended or unwanted behaviors that can ultimately lead to some leakages of funds or malicious behaviors. Yeah, we can also wrap the code with some systems that can prevent that part and enforce the contract with some specific directives that here comes an enhancement, right? So we can have already some contract that we want to enforce with some additional, wrappers so that you can't do things you couldn't do, you didn't want to. Yeah, so essentially this is the directions we're heading to for as far as the process analytics is concerned. There is another part which belongs to the chain, on-chain and off-chain computation. Applications that run based on blockchain may not be able to work alone, yeah, because the blockchain is a sort of closed system. You have in mind how the blockchain works if you think of it as an isolated system in which things happen and they're stored. So if you store the stuff that is on chain, then it remains on chain. But for instance, a contract natively cannot, repeat that, cannot natively invoke an off-chain service. So a contract cannot know from, I don't know, even CoinMarketCap, how many dollars is an Ether worth, because it would mean that you call from within the blockchain something which is outside. That's basically a protection mechanism, which makes it also possible not to have points of attack, because if you let the contract call something which is outside the blockchain, then all these system mechanisms that you put in place to avoid that there are malicious intentions, that you validate all transactions and so forth, they also depend on things which are off-chain, and therefore all these protection mechanisms just fall. That's why we have the so-called oracles. Oracles that are also being used for instance, like insurances, but it could be basically also the way to tie together internal things, so operationally working systems that are outside of the chain, which do not have maybe too many resources at hand, so they cannot be full-fledged or even light nodes for the chain and the blockchain together. They're called oracles because they let, such as the oracle in the matrix, right? They let you know what's going in the sphere you don't know. So if you're on chain, they can tell you what's happening off chain, but if you're off chain and you don't have access, could be, or cannot interpret what happens on chain, they do the same. In this case, with Etherisk, they have created some oracles that could dictate if a flight was late, and if a flight was late or cancelled, then automatically the insurance through the smart contract would pay you in a given amount, just as a flight insurance. Yeah. Now, as I said, the problem is that you can't invoke from within the chain the off-chain systems, so that's why we have the oracles, and they act as a bridge. What we have observed is that much of the efforts have been spent towards the inbound chains, inbound oracles that dictate what happens off-chain to the on-chain environment. So they tell the contracts what's happening outside. But you know what? That's not only the inbound communication. There is also an outbound communication. For instance, imagine this: if you pay on-chain, you automatically unlock the entrance to a rented flat. Could be, right? Well, in that case, what's happening on chain has a side effect off chain, and again, it's a sort of oracle because the door is not connected to the chain, but perhaps oracles can be software systems that turn what's happening on chain, the activation of a smart contract function, onto the physical world, even sending email if you like. Also, depending on who's the initiator of the communication, it can be a pull-based or push-based communication, right? So if it's the contract willing to know what's happening outside, it's a pull-based inbound. Yeah. If the door wants to know if someone paid for it to be open and unlocked to this user, it's a pull-based outbound. But if you want the contract to push, then and there are also the differentiations for oracles. They can be software or hardware. They can be also human oracles. When you have like opinions, polls, surveys, certifying a given amount of information, can be also other blockchains being used as an oracle. Why not? They can be centralized, decentralized. So we have been investigating a few of those mechanisms. And we have observed that typically, however, the additional costs and time that they require, they are typically tractable because they wouldn't really interact in terms of invocations, but typically operate as reactive systems that sniff for given transactions that have some logging systems inside and therefore operate accordingly. Okay, so long story short, what we have seen is that there is a huge amount of information that we can use to run, sorry, let me get back to, yeah. To run process mining, process management. So to manage processes, production processes, or economics processes, whatever you like, you name it, on chain, with the aid of blockchains from a myriad of perspectives. Could be for the automation side, could be for the check-in side, for the discovery side, for the oracleizing side. There are many more of roads to investigate. And if you want to know more, please do not forget to contact us. I'm very happy to have a chat with you. So I was a bit out of time, I think, like.
Yeah, it's all right.
But if you want to know more, here there is a list of publications, and also, yeah, mysurname.net is the website you might want to give a hit to.
Thank you, Professor.
Thank you for the opportunity. Thanks.
Do we have any questions, or shall we close the session?
Well, I think
So, no questions. Thank you, Professor.
Thank you.
Thanks also our participants. Our sessions will continue tomorrow. We have very interesting topics tomorrow and all the week. It was very nice to see you here today. Thanks for your time. Have a nice day.
Thank you so much for the opportunity. It's been a real pleasure as last time, but also this time and next time. Looking forward to the next collaboration. And thanks a lot. Talk to you soon.
Thank you.
Have a great day. Bye.
Bye, everyone. Thank you.